Vaibhav, are you in office? You are muted.
Yes, sir. I am at office now.
Okay, so we'll start in
Yeah,
4 minutes. Some more.
yeah,
Still there are 2 minutes to begin with, and
correct.
there are some people are joining.
I think our first speaker is here. Uh,
Yes, that should be me if I'm not mistaken.
yes. If I am pronouncing it correctly, is Magdalena.
Mhm.
Yeah,
So just wait for a few minutes and
yeah.
someone will. It's not just 6.
Meeting is being recorded.
Okay, it's 6 o'clock and it's time. As 6 o'clock at India, but not at the place of the speaker. But it's time to start so that we can move as per the schedule. So still people are joining, and I believe that just when we begin slowly, by then some more people will join us. So welcome you all to the third day of our International Young Quantum Scientist Meet. And except me and the inaugurator, everybody is pretty young here. And today's session chair is Dr. Vaibhav Raut, who is a young particle physicist with a strong interest in many aspects of theoretical physics, including measures of entanglement. So lately he is, though by training he's a particle physicist, lately he is working on tripartite measures of entanglement, but he is not a speaker. Means he's supposed to chair the first session. And over to Shandip, over to Vaibhav for
Okay,
conducting the first session of the third day.
okay. Thank you, Professor Pathak, and thank you for the opportunity to chair the session. We had two wonderful days of this young quantum science scientist meet, and I think it is exceptionally motivating for young researchers across the globe to share their work. And we are delighted to have our first speaker for today's session from Czech Technical University, Magdalena Peryazkova, and she will be talking on phase instability of input states and Gaussian boson sampling. So let's welcome Magdalena, and over to you. You can begin your talk.
Okay. Yeah, thank you very much. Just a
Hmm.
detail, I can share a screen at the moment.
Just
Okay.
try to share. Means if there's a
Yeah,
permission needed,
yeah.
I'll give you the.
Give us a minute.
No, I have to give a
Yeah.
permission. You just try to share, then I'll provide the permission.
Okay. Can you
Okay.
start
Can you
sharing?
try?
Yeah, I can't. It shows me that the host disabled attendee screen sharing.
Okay, let me check where it is. Means it's no request for. Oh, okay.
Oh,
No, it's coming for.
do you see an option for send request, Magdalena?
No,
Oh,
no.
I'm just looking for the settings. It's not.
from
Yeah,
my
I'm
side.
also.
No, you cannot do it. Means I have to do it, but I'm not getting the option. Post tools. Okay. Now, okay. Now it's coming.
Okay.
Post tools for. Size. I'm sorry, means this is delayed from my side. Means just
Yeah.
application. So now it is done. Please do it.
Okay. Okay, you should be seeing the screen.
Now we can see your slide, but it's not in full screen. You have to make it full screen.
Okay. Now it should be.
Request other participant to keep muted.
So I have muted everyone. So I request the speaker to unmute herself.
Yeah. So Magdalena, can you please unmute yourself? Your screen
Okay. Yeah.
Yeah, your screen is still not in a full screen mode. So
okay. How about now? Is it better?
No.
No. Okay. That's apparently okay. Let's go for the backup option.
You can see the left side, but there are some certain things in the right side as well.
Yeah.
I will try this one. Okay.
But still, we can see the left hand side, the list of slides. Means it's not.
Is this better?
This fine. Means okay.
Yeah.
Please go.
Yeah.
Okay. Okay.
Yeah, this one is better.
This one is better. Yeah, it turns out there's apparently a slight issue.
Yeah.
With the. Yeah, this should be fine.
Yeah.
Hopefully, I hope. Sorry for the delay from my side now. Okay, so I will start. My name is Magdalena Parízková. I'm from the I'm from the Faculty of Nuclear Sciences and Physical Engineering at the Czech Technical University in Prague. I am a PhD student there, and I will be presenting my work together, which I did together with Craig Hamilton and Igor X. And I would also like to thank for the opportunity to speak at this event. With that being said, I will just move quickly. So I'll be talking about input phase noise in Gaussian boson sampling. More specifically, I will be talking about the part of my work where I did, basically I studied simulating noisy Gaussian boson sampling setup with tensor networks, more specifically matrix Virac states. So I will first introduce a little bit about Gaussian boson sampling and the phase noise problem. Then I will talk about matrix Virac states and operators and entanglement entropy and how does it relate to the complexity of such simulations. Then I will say something about my simulations I actually did and the results which we obtained from that. And then, of course, some summary and further work, just a teaser towards what didn't make it to the presentation. So with that being said, about Gaussian boson sampling, you have probably heard about it. If not, it's a non-universal model of quantum computation for bosonic system. It is basically a variant of boson sampling with Fock states, which was introduced by Aronson and Arkhipov. But this time we take Gaussian states as input states, and that changes a little bit of things. Okay, so just to be clear, Gaussian states, I mean states whose Wigner function and Q function is a multidimensional Gaussian function. And I will be also using in the simulation the most common state which is used for Gaussian boson sampling, and that is single mode squeeze vacuum states. Basically, if you have seen them, they can be represented also by basically taking a Wigner function Q, which is the one on the picture on the top. And as you squeeze them more and more, you basically literally squeeze the Wigner function. Of course, the state has many other properties, but this is just a visualization for those who see it for the first time. As for the actual setup, you take the Gaussian input states and you put them into a large interferometer represented by some unitary U. And then you just measure the output with photon number resolving detectors. And the whole Gaussian boson sampling problem is the actual sampling from the probability resulting from such setup. The probability distribution is given by a function called Hafnian, which you can see over there, which basically takes a matrix and calculates a number. The matrices are submatrices of matrix A. The submatrices are chosen based on the output pattern, basically how many photons you measure in different modes. And matrix A basically encodes the output state in the sigma Q, which is a covariance matrix of the output state. What is interesting on it is that if you If certain conditions are met, more specifically the collisionless regime, which means basically that you have much larger interferometer than you have the number of input states, sampling from this distribution is a classically hard problem. And it's based from the fact that calculating a Hafnian of a general function is a classically hard problem. So this problem was originally introduced as a quantum supremacy candidate. However, over the years, it kind of developed also other uses, for example, for many different graph problems, also for example, vibrational molecular spectra, or also preparing, if you adjust the setup a little bit and post-select then for creating states such as GKP states. So with that being said, there has been many experimental realizations, which probably you may have heard about some of them. However, they have all one thing in common, and that is significant amount of noise, which is present in the system. The main issue is photon loss. However, there's also problems with partial distinguishability and phase instabilities, depending on the architecture used, which of course inspired a number of works on classical simulations which are efficient, and also many benchmarking methods for these kind of devices. For photon loss, of course, which has been studied the most, one of the most popular and successful classical simulations has been done via tensor networks. And you can look at the paper mentioned below. And that is also one of the reasons why we will be looking into tensor networks today. As for the phasing, because I said that I will be dealing with the phased input states, I should probably define that, right? So I will be taking the input states and I will be applying a general dephasing channel on them. This is a channel which you have probably seen before. It's not anything novel or new. The only important thing is probably the phase distribution, which is chosen according to the model you are using. So one of the most popular choices, or more simple choices, is probably a fully phased case represented by uniform distribution. This is the worst case scenario. So basically what you get in the end is, sorry, is a statistical mixture. And okay, this is not expected. Okay, it basically gives you a statistical mixture. Only the diagonal terms of the density matrix survive. As for the wrapped Gaussian distribution, you will get a sort of a Gaussian, so something in between. What you have to do with the Gaussian is to make it periodic. So that's basically the sum over here, because you have an interval over 2 pi instead of just a whole spectrum of real numbers. And this results in a prescription for the output state, which basically takes the off-diagonal terms of the matrix and exponentially diminishes them if the phase noise increases. And in the limit of large sigma, you will get a fully dephased case as for the uniform distribution. Just a note on the side, general effect on the probabilities can also be kind of taken out of the actual probabilities, and you can dephase kind of the final probabilities. But that's just a teaser, a note for the end. We will not be using this in this presentation. So, as I have said, basically what we will be doing is that we take the same setup, just on the input states before they enter the interferometer, we put the dephasing channel and let the sampling proceed as usual. For networks, we will be simulating the system with tensor matrix product states. This is basically that you take a multi-body quantum system and its state, you take the amplitude, probability amplitudes as some large tensors, and you split them into a lot of smaller ones. So basically you cut them into this sort of chain of like one-body tensors, which have some sort of additional information about the interaction between those bodies. So we will be decomposing this basically input state, which is actually already decomposed, because for separable input states this is already done. And then we will take our interferometer, we will decompose it into a lot of layers of beam splitters. Your decomposition is, it doesn't matter if you choose Rex, Clemens, depends on you. And then we apply this to local operations basically in series. And it turns out that this is very efficient with matrix product states and operators. So that is the reason why the simulation goes this way. The important parameters also is the local dimension, which is our cutoff on the Fock space, and bond dimension chi, which will turn out is related to entanglement present in the system. And we will also be, there is a reason why we chose this specific decomposition. We will be needing this, these lambdas, which actually has a physical interpretation. And by that, I mean that if you choose lambda k for a specific k, you will get a vector of Schmidt coefficients for different bipartitions of the system. So basically, if you take the system and you split it at mode k into two parts, you will get Schmidt coefficients. And these Schmidt coefficients can be used to calculate Rayleigh entropy or Rayleigh entanglement entropy, which actually can be related to the complexity of such simulations. So if you take a system and you scale its size, so basically n here represents for us the number of input modes, and if you and also you enlarge the interferometer as you go. So not only the number of input modes increases, but also the size of the interferometer. So you have like roughly the same type of system. And if you go into large values of n, so like asymptotically large sizes of your system, you can see how does the Rayleigh entropy behaves. And it turns out that if it's logarithmic or sublogarithmic, it means that the simulation using tensor networks is easy. However, if you go to linear scaling and faster scaling, it turns out that simulating the system this way is inefficient. So yeah, there is a little note because I have been talking about pure state so far. However, we have systems with noise. So we have mixed states and we have density matrices instead of a state vector. And density matrices, basically what we do with them is that we vectorize it, and then we use the matrix product state formalism on it, and we call it matrix product operators. Everything is fine, everything is nice, except for one thing, and that's the fact that now tensors lambda k represent the following coefficients, as you can see in this formula. And if you calculate the Rayleigh entropy from them as before, you will not get directly a measure of entanglement. You will get something called operator entanglement entropies, which contain not only entanglement, but also like some additional correlations. And efficiently, they will give you only the bound on the hardness of the classical simulations. So basically only this red part will be valid for the future directions. However, that doesn't concern us because we will actually be in this red point. So as far as the actual simulations, what we take is we take an average entanglement entropy over many, many random unitaries, and then we basically see how does it behave with the increased size of the system. So this is the number of input modes, so that's our n, and we study the scaling of entanglement entropy. This is actually a recreation of results for photon loss to just give you an idea how does it behave for different noises. So for photon loss, you can see that it very quickly loses the linear scaling, and it can be actually shown that it is true in the asymptotic limit, not just in the very few 10 modes. However, this is also a uniform phase loss, and the full results you can see in this paper. What I did was look at the dephased system. So basically, as you can see, that this is a graph for Gaussian phase noise with different variances. So basically, this is the ideal case, and then you go to the red one, which is the completely dephased state. And you can see that although the values overall decrease, the scaling remains somehow linear, and it holds even for different squeezing as long as you are in the collisionless limit. So basically, this is an indication that it might not be the same as the photon loss, and it turns out that it actually is, because this linear scaling will prevail. Also for the cases when you, in this case, what I did is that I took the variance and I increased it with the size of the system, which is the case for photon loss. So I made it even worse for cases when you like increase the size of the system. And you can see here that everything eventually boils down to the uniform phase distribution. And that means that if we can prove that the uniform phase distribution results in a difficult problem for this matrix product states, all of these distributions will be a difficult problem. And that actually turns out to be true. You can show it analytically. I won't go into details. So unlike photon loss, which results in these types of scalings, depending on the parameters beta and gamma, you will get for all of the phase distribution, even and dependent, you will get linear scaling, which means that this kind of simulations using matrix product states and operators is not an efficient way, unlike for photon loss, to simulate this kind of system. And just a note, if you combine phase noise and uniform photon loss, you will get the same results as for photon loss. The scaling remains the same. The phase noise just like diminishes the actual like numerical value. So with that being said, we are getting to the end of my presentation. So as a summary, just to like few main points. The losses may Gaussian boson sampling classically simulatable that has been shown, for example, by tensor networks, as I have mentioned before, with matrix product operators. The complexity of such simulations is related to the entanglement entropy of given state. For matrix product operators, it is operator entanglement entropy. And for the phased input states, we showed that the system stays inefficient to simulate wire tensor networks, unlike for photon loss, which is quite an interesting thing to see. And as for some future works and further work, which didn't make it here, we also look into some properties of these dephased final states. We look at other classical simulations, which might somehow use the dephasing a little bit better, because apparently, like, this is not tensor networks do not use all the advantage that the dephasing can give us. And also, it is interesting to study the sensitivity of the resulting probabilities, correlations, and other measurable variables to phase, both from the point of like benchmarking and actual measurements. And with that being said, I thank you for your attention. And if you have any questions, let me know.
Yeah. Thank you, Margasina, for finishing perfectly on time. And we have some time for the questions and comments. I request participants to please unmute and they can ask their question. You can raise your hand.
You can also unmute yourself and just ask a question.
Yeah. The participants, please feel free to ask questions if you have any. So if meanwhile, I have just one small question. I mean, when you're talking about the complexities of the simulation, and the Renyi entropy is one of the I mean, I would say benchmark in testing the complexities of the simulations. I mean, in that scenarios, are there any other measures other than Renyi entropy that can serve that purpose, and why Renyi entropy in particular?
I'm not sure if for matrix product states in particular, there are other measures. I haven't seen them. However, the reason that there is a lot of unstudied parts of this, like it's not fully known yet. And as for example, as I have been showing those two parameters, D and chi, right? So the cutoff basically it doesn't usually trouble people, so it is not much studied, like how does it influence the complexity of the system. And for example, for me, it was actually making quite a lot of problems, unlike for photon loss. So that's another question which kind of arised. But as for the chi, that is actually, it can be shown that it's related to the amount of entanglement present in the system. And it kind of makes sense because the more like interaction and entanglement you have in the system, the more you kind of need the information, the larger the tensors needs to be. And this can be very well measured by directly Rayleigh entropies. So that is the reason why that goes here. For matrix product operators, as I said, that's an issue, right? Because the proper measure of entanglement for mixed states is a big problem, as I'm sure you know.
Okay. Thank you. I mean, students are encouraged to ask questions. You can unmute yourself. Is there anyone who you can raise your hand? Yeah, Shivani, do you have a question? Yeah.
Hi, Magdalena. Hi. I just wanted to ask you, how is the future of this work looking like?
Right
Are you
now,
also doing the estimation? Yeah.
the estimation?
Yeah. You're also doing the estimation of these losses?
You mean with that's important to note that this work was actually inspired by an experimental group, which we are collaborating with. And yes, there has been a few discussions, but it's very early on. So far, we have been looking mainly into correlations and how does it affect the probabilities. But yeah, estimating the losses it's a plan for the long run so far.
Yeah.
Okay. Thank you so much.
So yeah, so we owing to the limited time, we'll move to the next speaker of this session. Thank you so much, Magdalena, for a wonderful talk and participating in this meet. And our next speaker, we have Dr. Shruti Agarwal from Delhi Technology University. She will talk on characterizing Jungian 3-qubit entanglement via concurrence field. Yeah, so Shruti, I can see her. Welcome, Shruti, and you can share your screen.
Good evening, everyone. Am I audible?
Yes, you're perfectly audible.
Good evening, everyone. I'm Shruti Agarwal from Delhi Technological University. Today, I will be speaking on characterizing genuine 3-qubit entanglement via concurrence field. Firstly, I would like to thank the organizers for giving me the opportunity to speak on my work. So entanglement, as we know, it is a fundamental resource in various quantum information processing tasks such as quantum communication, quantum computing, and quantum cryptography. It was first discovered in the EPR paper, and Einstein called it a spooky action at a distance. Quantum entanglement enables particles to affect each other even if they are far apart. Since entanglement is used as a resource and it is a purely quantum mechanical phenomena, its quantification characterization is an important problem in quantum information theory. So I will be talking about multipartite entanglement. So in multipartite systems, if we talk about the tripartite system, the states can be classified as separable, biseparable, and genuine tripartite entangled states. So mathematically, we can represent a fully separable state as convex combination of product states of individual subsystems. Similarly, biseparable states are when the two parties are entangled and they make a group, and and they are not entangled with the third party. So mathematically, it can be represented like this, where xi's are the states of the system X, and phi i's are the represents the states of the entangled states of the system YZ. Asen et al. Classified 3-qubit mixed states into 6 SLOCC inequivalent classes. So these states cannot be converted into one another even after applying stochastic local operations and classical communications. So these states are fully separable states, which we can see in this schematic diagram that it forms a convex subset of the set of all 3-qubit states. And these 3 leaves represents biseparable states in A BC cut, B AC cut, and C AB cut. And the outside of this lies the genuine entangled states, which can be classified as GHZ and W class of states. So quantification of entanglement is a fundamental problem in quantum information theory, and it is important because there are very rare methods to quantify entanglement. So genuine entanglement, multipartite entanglement measure, or a GME has to satisfy some conditions. Firstly, it should be 0 for all biseparable and separable states. It should be non-negative for genuine entangled states. It is independent of the local unitary transformations, and it must be LOCC monotonic. So if we talk about bipartite entanglement measure, concurrence is a well-defined measure which has an elegant formula which was given by Wouters. So it can be represented in terms of the eigenvalues of rho tilde, where rho tilde represents the flipped density matrix. This can be reduced to, for pure state, this can be reduced to this expression, which is written in the form of determinant of the reduced state. So for concurrence, we have this formula for 2-qubit system. For higher dimensional systems, there is no closed formula yet given, and one must rely on the lower bounds to quantify the amount of entanglement. Now in tripartite system, we have one entanglement measure which is called 3-tangle. So 3-tangle is a consequence of the monogamy inequality. So it is the residual entanglement which is represented in terms of the bipartite entanglement and the entanglement in the composite systems, 2 composite systems, where here the C square ABC represents the squared Wouters concurrence. So tangle is 1 for GHZ state, and the value is 0 if the state is separable, biseparable, or it belongs to W class. So from here we can see that tangle is a well-defined measure, but still it is not able to classify W class and GHZ class of states because it cannot detect W class of states because it is 0 for W class. Next is partial tangle, which is a measure of residual 2-qubit entanglement in a 3-qubit pure state. The formula is given in terms of 2-qubit concurrence and squared bipartite concurrence. So partial tangle can also help classify entanglement structure. So if partial tangle vanishes, or all the partial tangles vanishes, it is a fully separable states. If at least one is 0, then it is a biseparable states, and if all are non-zero, then it is a genuine tripartite entangled state. And now since tangle is not able to classify the W class, we have another entanglement measure which is called concurrence spill. It was given by Zai and Eberle, and this is based on the entanglement polygon inequality, which says that one entanglement cannot increase the sum of the other. So this is calculated. It is a consequence of the area of this concurrence triangle. So in this, the vertices are defined by the particles and the edges define the squared bipartite concurrence. So it was shown that concurrence spill can be if we calculate the area of this concurrence triangle. So we get a measure which satisfies the properties of genuine multipartite entanglement measure, and it is called concurrence spill, and the formula is given here where Q represents the semi-perimeter of the concurrence triangle. So this is 0 for all separable and biseparable states, and it is 1 for GHZ class, and for W class state, it is 8/9. So this formula is also given for the pure states. Now this problem is challenging because for mixed states, there is no concrete formula or no concrete criteria given which can measure the amount of entanglement in higher dimensional or in multipartite mixed states. So Zion and Burley also express concurrence fill, but it is also given in terms of pure states. We in our work formulate this concurrence fill in terms of tangle and partial tangle, and it is shown in literature that tangle and partial tangle has some operational meaning because it can be estimated using it can be measured using expectation value of measurement operators. Also, this work extends to mixed 3-qubit states of some particular types. So firstly, there are some results given which can classify GHZ and W class of states. So first, in the first theorem, we represent concurrence fill of a 3-qubit pure state in terms of tangles and partial tangles. The proof has a lot of calculations, and it can be seen in the paper published in International Journal of Theoretical Physics. Next, in this theorem, we say that if this inequality holds, if you have a 3-qubit state psi ABC, and if this inequality holds for W class of states. Next, the corollary says that if this inequality is violated, then the state belongs to GHZ class. So this we have shown with the help of an example. So we took this example with of 3-qubit pure state with 4 parameters, and in case 1 we choose such that it is a GHZ state, and we show that using the criteria also it is satisfying the properties, and the inequality is satisfied, and the inequality in the corollary is satisfied, and it belongs to the GHZ class. In case 2, if we check the inequality, it is shown that the inequality is violated, and hence it belongs to W class. So this can be seen in this diagram also. So in the first figure, in the second figure, this LHS is less than RSS, so it belongs to GHZ class, and in the figure on the right hand side, it belongs to W class of state. Next, we defined concurrence fill for mixed states. So if rho is a mixed state, the concurrence fill can be defined as a convex loop extension of the concurrence fill of the pure states. Here, minimization is done on all pure state decompositions. Now, convex loop extension is a cumbersome process which involves a large amount of optimizations. So one has to find optimal ensemble. So an ensemble that minimizes the average value of the particular entanglement measure under the construction, it is called optimal ensemble. If we see the spectral decomposition of a rank R density matrix, and we can express it in terms of the eigenstates of the density matrix, any other decomposition can be obtained from this spectral decomposition using a unitary operator. So using this, we can say that concurrence fill of all pure states can be seen as a fingerprint to find the concurrence fill of the mixed states. So using this approach, we consider firstly rank 2 mixed states. We are not considering all the tripartite mixed states. We are considering particular rank based states which are rank 2 mixed states, and these are the mixture of generalized GHZ and generalized W states, where generalized GHZ and generalized W states given like this. A, B, C, D, F are constants which satisfies the normalization condition. So to study the concurrence fill of this family of mixed states, firstly we consider the concurrence fill of the superposition of eigenstates of these mixed states. So the eigenstates of these mixed states superposition are given like this, and we obtained the concurrence fill. We derived the concurrence fill for these pure states, which is given in this form. Here, for generalized GHZ state and for generalized W state, the expression for concurrence fill is given, and these plot shows For symmetric, for some particular case where the states are symmetric, where A and B is 1 upon root 2 and CDF is 1 upon root 3, and for different values of phase, how does the eigenstates are behaving? How does the concurrence fill of the eigenstates are behaving?
Shruti, sorry to interrupt. You have 2 more minutes.
Okay, so in the next, our aim is to find the minimum value of the of concurrence fill for the eigenstates. So in this result, we found a lower bound for the eigenstate for the concurrence fill of the eigenstates, and we show that if we take a particular example of symmetric GHZ and symmetric W states, the concurrence fill coincide and with the minima, and it is equal to 4 by 5 with the value of P star equal to 2 by 5. Next, if we see the block sphere for the two-dimensional space that is spanned by the GHZ and W state, we can see that this forms a tetrahedron, and this tetrahedron with Z01 and Z02 and W state, this contains all the density matrix with zero tangle. So using this, in this polytope, we found the expression for the concurrence fill, which is given in equation 28. And we are not able to find the exact expression of concurrence fill for this mixed state. We have found an upper bound, which is given in equation 28, which is in terms of the eigenstates, the concurrence fill of the eigenstates and the concurrence fill of the generalized W state after finding the optimal decomposition. So for symmetric GHZ and symmetric W state, this is the plot for concurrence fill. To summarize, we have addressed the challenge of detecting and classifying 3-qubit genuine entangled states. And to achieve this, we have studied concurrence fill as a measure for pure as well as mixed 3-qubit states. Firstly, we have reformulated concurrence fill in terms of tangle and partial tangle. Next, we have employed this to classify GHZ and W state. Lastly, we have applied this to analyze rank 2 mixture of generalized GHZ and W class of states. And we have shown that for the eigenstates of the resulting generalized mixed states, we derived a lower bound and an expression of concurrence fill and an established an upper bound for zero tangle mixed states polytope. Thank you all for listening.
Thank you for a very nice talk, Shruti. The session is open for the questions. Yeah, Priyanshi, if you can ask, unmute yourself. Priyansh, sorry. Priyansh, if you directly can ask a question by unmuting yourself. So, Shruti, there's a question in the comment. If one qubit in a 3 qubits entangled system is lost or measured, what happened to the remaining entanglement?
So if 1 qubit is lost, we get a 2 qubit state. So that 2 qubit state may be entangled or may not be entangled, depending upon the nature of the 3 qubit state.
Okay.
Okay, I have a questions.
Yeah, please go
we
ahead.
measure only 3 qubits state, and if this is entangled, this is 2 power raised to 3 states, and if we measure 100 qubits at a time, which method is used another than the states?
So this method is for tripartite state, and in literature it has been generalized to higher dimensional also, as we have shown that this forms a polytope in for tripartite. As we move forward in higher dimensions, it forms a quadrilateral kind of structure and another polytopes in higher dimensions. And if the number of parameters increases, the complexity also increases, as we know. But this is an analytical criteria, so one can apply this for higher dimension also. The generalized forms of these criteria are given in literature.
Yeah, if as you know, Google makes 104 qubits quantum computer, then which method they use to assure that their system is entangled, each qubit is entangled or not?
They can use the these are the analytical criteria. So these criteria work for n dimensional systems. So for if they are using n dimensional qubits, one has to extract features to apply into this. So this
Okay.
involves eigenvalues, and so for those states, they have to analyze first, extract those features, the eigenvalues and all the values in which it is depending. If they are able to extract those features, then this it can be applied for n dimensional. It can be applied in this
That ma'am,
in these
if
analytical
we have
formulas.
100
Sachin, we
okay,
due
only
to
one question,
yeah,
sir.
yeah.
If we have 104 qubits or 100 qubits, then its eigenstates extremely large and
Yes.
exponentially grow. So it is not used by classical computers to compute it. Okay.
Yes, it is a computationally hard as we as the dimension increases. That is why we need more and more criterias to, so that that is why we have to rely on sometimes bounds, upper bounds and lower bounds, because those are computable and
Okay.
in
Yeah.
minimum number of computations.
Okay,
There
thank
are
you.
two quick questions, if you can just quickly answer it.
Mhm.
Is concurrence invariant under all local operations or only unitary ones?
Concurrence is invariant under unitary local operations.
And there's one, if you can just briefly answer this question, what is the use of GHZ and his benefits and its benefits?
GHZ states are some particular class of 3 qubit states, 3 qubit or we can say n qubit states. So these are used in quantum information processing tasks. So I have not worked on like those applications, but I have seen papers where these states are used in quantum communication or quantum cryptography when n qubit system is considered.
Yes. So if there are any more questions, please you can write to Shruti, and then there can be some discussions over emails. Owing to the time limitations, we thank Shruti for a wonderful talk and joining this Quantum Young Scientist Meet. We move to the next speaker
Thank
in the
you.
today's session. That is Nripendra Muzumdar from Indian Institute of Technology, Tirupati. He will talk on absolutely maximal contextual correlations.
So till the next talk start, we request all the speakers to keep an eye on the chat room, and if there is a question in the chat room directed to you, please answer there just by typing.
So hello, sir. Is it visible? My screen is
Yeah,
No,
but
it's
it is not full
empty
screen mode.
space, means it's not full screen.
yeah, that I am doing. So now it is
Yeah.
okay.
So now it's fine. And if you have
Okay.
confidence about your internet, then switch on your camera too.
Yeah, that's why I am keeping my camera off. Is it off? My camera is off, right?
Yes,
Yeah,
yes.
yeah.
If you have confidence on your internet, then you can keep that on, and please continue.
Okay. So good evening to all. What?
Yeah, you can go ahead.
Yeah, okay. So good evening to all. My name is Nripendra Majumdar and I'm from IIT Tirupati, working under the supervision of Dr. Arvinda S. And today I'm going to talk about absolutely maximal contextual correlation. And my talk is divided into 3 parts. First, what are the motivation behind this work? And then what are the mathematical methods we are used and we have used, and then my results and calculations. So you can see this picture. So first I will talk about what do we mean by non-locality and contextuality. Now you can see this picture where we have 2 parties, Alice and Bob, and they have access to one of these 2 particles which are somehow which has a previous interaction between them, and now Alice is having one of the particle and Bob is having one of the particle, and this can be this can be mapped into 2 boxes where if you give some input to one box you will get some outcome as x1 or x1 prime. Then taking this picture, we can always able to get these joint probabilities corresponding to the given input, and then the corresponding measurement and the corresponding outcome, or what is the joint outcome given the input. We can always able to get these joint probabilities. Now, these joint probabilities, like this box, you can see this is a point in a higher dimensional space. So it makes a polytope. And all these correlations are non-local if these correlations are non-separable. And also, if they using Bell inequality, you can say when the correlations are non-local or local, using the bound, this bound for bipartite system. So when it is less than 2, then the correlations are local, and if it exceeds the bound, then those correlations are non-local. Now the point is that this inequality is a contextual inequality in the sense that the measurement outcome always depend on what kind of measurements are you performing alongside with the other measurements, which we call context. So each term here, x1, x2, the joint measurement x1, x2 or x1, x2 prime, these are called context. And the outcomes always depends on what kind of measurement are you performing. Let's say with x1, what other measurements you are performing. So that is basically contextuality says. And here you can see that the entangled state means the state is entangled when you cannot write in a product state. Similarly, in non-local correlations, you can say that you cannot return in their marginal probability product form. Now, to define the entanglement for multipartite system is quite difficult, and people are exploring it. Also, there is a interesting concept called maximal entanglement, which is for bipartite system. There is only one such class exists, which are Bell states, and for 3-qubit system there are 2 such class, which in the previous talk she mentioned that one is GSZ and another one is W class. And then using different operations like LOCC or SLOCC, you can convert. Like LOCC you can convert from one entangled state to another using either entanglement distillation and entanglement transformation, and its quantification is much more difficult for multipartite system because the parameters involved in the unitary evolutions gets increased with the time. And then we ask, like, how can we define this maximal form in entangled state for multipartite system? The similar question we can ask in correlations, because this LOCC, this LOSR is the analogous of LOCC in correlation terms. And in multipartites, in a more general sense, one can use the WCC PI. And then we ask, like, in one of the recent research, they have shown that even in the asymptotic condition, you cannot go from like non-local state to like local correlation to non-local correlation, even in the asymptotic condition. So then we ask, like, how can we define this maximal form in the correlation for multipartite system? So to understand that, we have taken the correlation which is analogous to Ame state. Now, to understand those correlation and to define those correlation, we use the Schiff's theoretical method, and which defines this experimental setup or operational setup using 3 variables or 3 sets, where X is the set of all variables which Alice and Bob are performing for bipartite system. And this M is basically we call measurement covered, which is a set of all the, or you can say family of all the contexts which we have seen in the previous inequality. And the outcome set, which is defined as for bipartite, we are taking it is a dichomatic measurement. So the outcome set is always 0, 1. And then depending on the context, we have these outcome set for each so for each context, we have 4 such outcomes, which we are calling sections or local assignments. And corresponding to this set where we have all the measurements in one set corresponding to those independent of the context, the outcomes we are calling is global assignments. Now, any experimental or any operational setup can be defined using these three sets, and the previous this operational view or this table can be mapped to this linear form where M is a matrix of dimension n cross n depending on dimension of D and V. Here D is basically those global probability distribution corresponding to those global assignment or global outcomes which I have defined previously, and V is basically the probability in this table which Alice and Bob are basically getting. So understanding this concept, like what do we mean by contextual and non-contextual, if you are able to find out the solution of this linear equation, which is D, which is having any non-negative solution, then the model is contextual, otherwise it is non-contextual. To understand that, you can see this cartoon where I'm saying that the bucket is full of grains. These yellow things are grains, which is coming from this bigger bag. But we are asking, like, having these two buckets with the Alice and Bob, which are local probability, joint probability distribution, we are saying, non-local, but they are getting in their labs these probability distribution, which is that joint probability distribution. Then given those probability distribution, can we say that this bigger container exists or not? If that bigger container exists, then we say the model is non-contextual, otherwise it is contextual. Now, any model like that operational view I showed you in the table of Alice and Bob can be written in the convex decomposition of non-contextual model and strong contextual model. What do we mean strong contextual model? That depends on these factors which we are saying. The non-contextual fraction is equals to P and contextual fraction equals to 1 minus P. If P is 0, the non-contextual fraction is 0, and if CF is 1, then we are saying that model is basically maximally contextual model. And the examples are, you can see the Bell state, if you take for certain measurements, then contextual fraction is 0.25. That is not 0. That's why we are just saying it contextual. But when you go for PR box, definitely it will give you contextual fraction 1. So it is a maximally contextual model. And now we have defined our correlation, which we call maximally contextual correlation, which is basically which shows CF equals to 1, means those correlations are maximally contextual as well as maximally marginal. Why they are maximally marginal? Because if you take their reduced boxes, then you will always get all the outcomes all the joint probabilities are equal. Now let's say, let's take few examples. For PR box, you can see these are the marginals of this form, which is having all the joint probabilities are equal. So this is maximal marginal, and for this CF is also 1. So this is for 2-2-2 scenario. This is basically an AMCC. Now, if you go to 3-2-2 scenario, then this GSZ correlation is also AMCC, because you can see the marginals are maximally random. Now, there are examples where we can see that there are non-AMCCs which show CF equals to 1, but they are not maximally marginal. Now, to get more to generate such kind of correlations which are AMCC and non-AMCC, we have reduced the parameter of this 3-2-2 box, which usually contains 64 parameters. And since we are only taking the no signaling boxes, then further it reduces to 26 parameters. And now, using these three conditions, if you use no signaling and normalization constraint and the maximal marginal condition, if you take, then by construction, we are able to reduce it to 8 parameters. And depending on the condition for these 8 parameters, we get different CF values. And for some conditions we get the AMCC as well, depending on those 8 parameter values. Now, how to construct those these AMCC correlations? For that, we are using two models. One is CSP model, another one is another one is this parity check method. So in CSP model, we can always map a probabilistic model to a possibilistic form where each non-zero probabilities we are making one and other we are keeping 0, and corresponding to this table we are always able to write these Boolean equations. And the another method we are able to see, we are able to construct using parity method, where we are taking all the measurements in a context, and by summing them, we are making equal it to some parity variable which take either 0 or 1. If it takes 0, then it is the parity is even. If it takes 1, then the parity is odd. And if you assign these parities as these values 0, 0, 1, this is for PR box, you can see. And for PR box, you can see this is the contradiction where if you divide by 2 here, then it shows 0 equals to 1, which is a contradiction. So whenever this kind of contradiction is there, so the corresponding possibilistic table will always show a maximally contextual model. So that's how we are able to define, and given these parity constraints, we are always able to reconstruct those Boolean equations. And if all the Boolean equations are simultaneously satisfied, then those models are also maximally contextual. So using these, we are able to construct few AMCCs which are non-symmetric as well, like similar to GSZ state. And this table we are able to construct using those CSP method we are using, and we are able to construct this table where we have only three independent variables, and these are probabilities.
Sorry to interrupt you. You have
Yes,
two more minutes.
Okay, sure. It's almost done. So for these boundations, this table shows always CF equals to 1, but that doesn't show that it is maximally marginal. But putting these particular values where P1 equals to P3 equals to 1/4 and P2 equals to 0, it is an AMCC. And all these these AMCC correlations we have used for secret sharing protocols as well as randomness extraction, which we have in this paper, which is in arXiv. You can look into it. Thank you.
Yeah, thank you, Nripendra, for finishing very much on time. We have some time for the questions. There's one question I can see on the chat box. How does contextuality related to the quantum non-equality?
What do we mean by quantum non-equality? That I wouldn't understand.
Mukarram, if you can unmute yourself.
You can unmute and ask the question instead of typing.
Yeah. Mukarram, Sufyan, or any other question, you can unmute and ask quickly. Students are encouraged to ask questions.
I'm dropping in comment my.
Yeah, can you just clarify some? Yeah.
Yeah, what is this quantum non-equality? What is that? Can you repeat once?
Like violation of Bell inequalities, like something.
Okay. So see here, what you can see that with in the later slide, I said that these joint measurements are basically context. Okay, so I'm saying that if you are assigning these measurements, there are 4 measurements you can see: x1, x2, x2 prime, x1 prime. So independent of this context, if you assign them values, let's say it takes either plus minus 1. So then what happens that if you independently assign them, they will never violate this inequality. that's how the non-contextuality is related to non-locality, and even non-locality is a special case of contextuality. So does it give it means answer for your question?
So, is there any other question for Dipendra? If not, we thank you, Dipendra, for talk.
Thank you, sir. Thank you.
You can stop sharing your screen. We move to the next speaker of the session, Faisal Farooq from University of Kashmir. He will speak on non-Markovian effects on the steady-state properties of damped harmonic oscillators. Faisal, can you start sharing your screen? Yeah, wonderful.
Is everybody seeing my screen?
Yeah, we can see your screen. Can you make it full screen?
Yeah, please.
If you have a strong network, you can turn on your video. Otherwise, you can start your.
I'll be keeping my camera off.
Sure.
So, hello everyone. I am Faisal Farooq, research scholar in the Department of Physics, University of Kashmir. So, I will be giving my this presentation on the non-Markovian effects on the steady-state properties of a damped harmonic oscillator. So, this presentation is based on our recent paper that was communicated last year. So, first of all, I will be we will see that we know that these open quantum systems, they exhibit a rich interplay between the coherent Hamiltonian evolution and incoherent dissipative processes. These incoherent dissipative processes make our ideal quantum system as open quantum system, which arise from the coupling to an external environment. So we know that this dissipation is always thought to be a limitation for us, but from the past years, we see that this limitation can be used as a resource. So this dissipation is now understood as a powerful resource to engineer and stabilize non-trivial quantum states, induce non-novel quantum transport phenomena, and we use these driven systems into controlled and non-equilibrium steady states. So we can see that in experimental advances, this dissipation has been used to engineer our quantum systems. So what will be our insight here is that we will be looking at how we can unlock our this approach to quantum state preparation, control, and study of non-equilibrium systems. So how can we control this dissipation and utilize so that we can unlock novel approaches to quantum state preparations? So first of all, we know that the dynamics of a dissipative quantum system is usually given by Lindblad equation. So this is the Lindblad equation. If we remove this L, we get our usual closed quantum system. And this L, which is called as a dissipator, is defined as this, where these L's are the Lindblad jump operators. So I will be using this Kaldich field theory technique. As we know that this Kaldich field theory technique is very useful in studying the non-equilibrium quantum states, and because it's tailor-made to study these non-equilibrium quantum states. Because in this Kaldich field theory, we usually do that. What we do is that we split our time in two contours. Forward branch contour and negative branch negative contour, which are obtained from this unitary operators, where one goes in the backward direction and other goes in the forward direction. So here we can see that by considering this Schrodinger and von Neumann equation, this is our usual Schrodinger equation. So using mapping this Schrodinger equation to a von Neumann equation, what we can see that we usually use this density operator. The evolution of the density operator is given by this unitary time evolution operator called as U, where it generates the evolution from t is equal to 0 to t, given by this formalism. So to obtain this Kaldich field theory technique, what we usually do is we try to decompose this evolution operator. We decompose this evolution operator by this formula. Then we perform this, we know this most general evolution of this density matrix is given by the quantum Monster equation, which has this quantum Monster equation has usually the solution of this form, where L is this Lindblad or dissipator. So we perform this totalization, and we I will not be going into the detail of this derivation. I will just be giving some insights into the derivation, what we usually do to derive our Cavendish path function or partition function. So we use this completeness condition for this coherent states, because this Cavendish formalism can be studied for this coherent states. Now we decompose the time evolution from t is equal to 0, t0 to tf in a sequence. We will be splitting our this time domain into smaller steps and denote the density matrix of the nth step as this. So this will be the density matrix at the nth step. Next, we will proceed to represent the density matrix in the base of coherent bases. Now we will be using this formula, and we will be inserting these identities into this density matrix to obtain the density matrix in terms of this coherent states. And now we will be performing the n is equal to infinity limit, and we will obtain this partition or this generating function, which is obtained by tracing out by taking trace of this density matrix. So we will get this formula where this S is the action and D is the integration measure given by this formula. And the Cavendish action, this S has the form of this, where this plus and minus signs are related to the forward and backward branch of the time, or forward and backward contour. And L has this form. So before introducing my model, we will have to look about some quantities. That is, when we study a model, we know that the model has some energy scale, our system has some energy scale, the bath has some spectral width, which is denoted by lambda, and this decay has some rate, which is usually denoted by this gamma. So the time scales are inversely proportional to this omega naught for the system, and for bath correlations, it will be inversely proportional to this spectral width. So to describe whether the system is Markovian or non-Markovian, we will be looking at these time scales, whether the relaxation time for the bath is less than this relaxation time for the system. If this condition is met, we see that this system evolves, system evolution dominates. So we have this Markovian dynamics. Otherwise, if this spectral or this bath correlation is very greater than this system correlations, we say that the bath memory persists, that the system has now bath because of this phenomena, that the relaxation time of the bath is very greater than this relaxation time of the system. So our system keeps track of its memory, so it has some memory, and this memory systems are called as non-Markovian systems. So Markovian systems usually have exponential decay of correlations, whereas these non-Markovian systems do not have this exponential decay of correlations. They have non-exponential decay. So we will be assuming our model as this harmonic oscillator, which is subjected to this bath, and there is a coupling between system and bath. Here we have not taken any rotating wave approximation. We'll be looking first in this non-rotating wave approximation, where this, and in addition to this coherent dynamics, we'll be having this dissipative dynamics, that or non-unitary dynamics, which is given by this equation as the dissipator, where L's are now replaced by this annihilation operator with having a decay rate gamma m. So this is a general form of this Lindblad equation, and we will be using this. Next, we will be mapping our system to the Cavendish for path integral, or we will be obtaining this Cavendish functional integral. So mapping using the formulas which we derived or which we looked at previously, we get the partition function or generating function, where these are the integration measures. And next we perform our K-list rotation, so defined as phi c, phi plus phi minus by root 2, and this quantum fields, classical and quantum fields respectively. Now we write this stringent K-list action in Fourier transform as this is the action for the system, this is the action for the bath, and this is the coupling. Why we have incorporated these dissipative rates or dissipator in this system or the bath. So for our system, this this action is given as this, and we obtain same action for the bath. Here epsilon is usually equal to 0, but we will be keeping this epsilon so that it acts as a regularization parameter. So we have to integrate out this bath. So to obtain the integration, we have to keep epsilon equal to epsilon there as a regularization parameter. So, and this is the coupling between the system and the bath. So we now integrate out the bath fields using the Gaussian integration to get the effective action for only system for the damped harmonic oscillator. We will be integrating out the bath and obtaining the effective action or effective this partition function or generating function for our system. So after performing this Gaussian integration, we will be getting a action of the form of this matrix type structure, where dr, dA, dKs are the retarded, advanced, and K-list components of the Green's function. This action has this causality structure because this are these classical fields which have to be equal to 0 to protect the causality structure, or we have to protect or we have to conserve the probability, where these are the super vectors defined as this omega minus omega, omega minus omega for quantum and classical fields. As we know that these are the retarded, advanced, and K-list Green's functions. These Green's functions can be expressly written as this. The full form of these Green's function are that this retarded Green's function is given by, after performing this integration, we obtain the K-list Green's function as this form, where this sigma is called this self energy. It is here because when we integrate out the bath, there is some effect of the bath which still is inside this system, which is dependent on, which is called as a self energy, and the full form of the self energy is here as Gk and omega k, where omega k are the frequencies of the bath, Gk is the coupling between system and the bath. Next, we define a bath spectral density of the form of this, so that we can be fully written as this. We take the Lorentzian shape of this spectral density, where this lambda is the spectral width of this bath, alpha is the coupling constant, and these quantities are well known. Now, after introducing this spectral density, we will be performing the integration of this spectral density to obtain the self energy for this Lorentzian shape of the spectral density.
Faisal, sorry to interrupt you. You have 2 more minutes.
Oh, I will be doing that.
Okay.
Next, we obtain this. Now we will be obtaining this spectrum of our system by taking the determinant of this retarded Green's function equal to 0 and get these following equations. Next, to study the to split our system, or to identify whether our system whether the bath is Markovian or non-Markovian, we will be introducing new parameters as Q and R's, where for Q greater than or very greater than 1 is termed as non-Markovian, and less than 1 is termed as Markovian. Similarly, we will be having this weaker condition for R. So writing this spectral or this self energy in terms of these Q's and R's and performing some approximations, we arrive at this equation. to get the stability of the system, we try to plot these roots. Here we have plotted the imaginary and real parts of the roots, where these dots are the imaginary lines and these solid are the real parts. So we have plotted these imaginary and real parts. What we see that as we go from R 0.11 to R 10, we see that first we have our system has once unstable root, but as we go from R less than or small to R greater, our system becomes stable. So to obtain the correlations, we will be using this formula, which is related to this Cayley's-Green's function, and using this identity to obtain this Cayley's-Green's function, and using this formula to obtain our number operator. What we see
Then
that
can you
yeah,
conclude in a minute?
yes, I will be concluding in a minute. I
Okay.
will just be showing my results.
Sure.
So what we see that, as anticipated from the previous graphs, we see that when we increase this R, there is no divergence in the number operator. For small R, there is a divergence which was seen from this roots. Here we see that when we increase this R, the roots become stable. Next, we will be studying this effect to temperature by using this fluctuation dissipation theorem, and we obtain this this effect to temperature as alpha, which is independent of Q and R. So our effect to temperature is directly dependent on this coupling. Now we will be studying these quantum Zener effects and anti-Zener effects. We know that this quantum Zener effects refers to the suppression of evolution of quantum system due to frequent measurements. Anti-Zener is its opposite. So using the formula above, we will be getting this formula for this quantum Zener effect in terms of this Cayley's-Green's function. What we see that our system first for R very less than 1, we have a transition between Zeno between anti-Zeno and Zeno parameter. But when we increase the R, the system resides whether in Zeno effect or in whether in Zeno regime or in anti-Zeno regime. So by tuning our this R, we can have the transition between Zeno and anti-Zeno. Similarly, we will be doing our whole calculation in this rotating wave approximation, where we will be neglecting these counter rotating terms and obtain the same what we have done earlier, obtain the same spectral self energies and roots. Here, what we see that for this rotating wave approximation, the system is cannot be made stable. There is an instability in the system for this rotating wave approximation, because the counter rotating terms which we ignored were able to make the system stable. But when we ignore this counter rotating terms, the system is not stable now. And for this rotating wave approximation, we see that for R less than 1, our system cannot have any transition between Zeno or anti-Zeno effect. So in conclusion, we have investigated damped harmonic oscillator with a decaying bosonic mode coupled to a non-Markovian bath using Lorentzian spectral density. Used Cayley's formalism, and we have defined quality factors to see whether our system, our bath.
Faisal, you can keep this slide open. Meanwhile, we can just take the question.
Okay.
Yeah. So audience can read the conclusions. And so, is there any question for Faisal? Thank you for a very nice talk.
Okay, thank you.
So, is there any question we have for Faisal? So, Faisal, I have a small question. What is a non-Zeno effect?
What is
non-Zeno region?
Non-Zeno.
Yeah.
I have not heard about.
No, but no Zeno effect, no Zeno The region was there in your plots, right? Somewhere?
No Zeno or non-Zeno?
No Zeno, no Zeno.
Okay, let me see. No Zeno means that we do not have any suppression or enhancement of this decay rate of this system. The system moves smoothly as it should be without any effect of this bath.
Okay. Are there any questions for Faisal?
Actually, I have one question.
Yeah, please.
In slide number, I guess 21 or 22. So they were question like you are showing T effective is 0. So actually, whether it is theoretically is 0 or like they are doing some experiment kind of stuff or reaching at that 0 Kelvin.
It's theoretical. It's not dependent on any system parameter.
Okay.
Yeah. Any other question? So yes. So if there are no questions, then we'll stop here. Thank you, Faisal, for a very
Thank
nice
you.
talk. This ends our session 1 of day 3. Thank you all the speakers for a very nice talk and all the audience who have interacted via questions and comments. We will be ending our first session here, and next session starts at 7:30 p.m.
Thank you, Dr. Weber, for conducting this session. So next session will start in 5 minutes. So in these 5 minutes, if any participant wants to ask any question or if he has any comment, then they are welcome.
Yeah. So if there are any interaction can happen in this. Yeah.
welcome back for the second session of the day 3. And this session will be chaired by Dr. Sudeep Haldar. So Dr. Sudeep Haldar did his PhD from University of Calcutta, and then he was a postdoc at many different positions, and right now he is working as a faculty in JP Institute of Information Technology, and his current area of interest include quantum many-body systems and applications in quantum information and quantum computation. So over to you, Dr. Haldar.
Thank you, Sandeep, sir, and I welcome everyone to the second session of day 3. This session is on quantum foundation. I hope I am audible, right?
Yeah, you are perfectly audible.
So now we are going to start our first talk of this session by Dr. Ramita Sarkar from Ariel University, Israel, and IOP Bhubaneswar. And the title of her talk is Persistence of Quantum Triality Relations in Open N-Dimensional Systems. So I invite Dr. Ramita Sarkar for the talk. Over to you, Dr. Sarkar.
Am I audible?
Yes, you are audible.
Yes, you are. And your slides are visible.
Okay. Am I visible also?
Yes,
But
you are
can,
also visible.
Okay. Thank you.
But you can make the
And-
camera a little down, means upper part of your face is visible.
Right?
Absolutely, absolutely. Please go on.
Okay. Mm. Good afternoon to you all. Today I am Ramita and thank you the organizer for this wonderful opportunity to present my work. Today I am going to present my work on this above mentioned title. So first I am discussing about the quantum triality relation and the motivation. We know from very beginning that is wave particle duality is a fundamental properties of quantum mechanics, and we are measuring this in a quantum or the system that is behaving like either wave nature, showing either wave nature or particle nature. We define the system as quantum, and we measure this quantity of wave nature like through visibility of the interference or simply visibility, and another is predictability, that which path which is what is the probability of the specific path the quantum will follow. Now there is a traditional complementarity relation, that is p square plus v square less than equals to 1. When it is 1 equals to 1, it is the duality relation, but sometimes it comes to the non-equality like inequality, p square plus v square less than. Why less than? Because the less than comes when really in the realistic scenario. What happened? Quantum is not an isolated system. When while it is going through the like it interacts with the detector, and while interacting through the detector or path marker, it generates correlation with the detector. And when we include the entanglement of that quantum and detector, then we have the extended relation, that is b square plus p square plus epsilon square, that is 1. Epsilon or epsilon square is the entanglement between the quantum and the detector. Now the main question of my work is, does this triality relation holds for the environmental noise? Is it valid? So first we start with the in-path interferometer system, and it is coupled with the detector state. Suppose we have in-path and in-detector, and the combined system can be written by this. And if we want to have the path state or the system state, we will trace out the detector state, detector part, and we get the reduced density matrix. And in this reduced density matrix, diagonal term gives the path probabilities, and off diagonal terms gives the coherence. Coherence is simply the coherence is like visibility, and the detector and the path overlapping controls the entanglement. Now we will quantify, that is visibility, predictability, and entanglement. And for the multipath interferometer in-dimensional system, we can define the visibility as B square, predictability and entanglement by these equations, where this rho is a density matrix, and we will here we get the trilateral relation. This will satisfy the trilateral relation. So for the first we will study from the two-path interferometric system. First we consider one pure path system. It is not entangled or correlated with the detector state. So we can simply write as a superposition of two paths, that is C1 Psi1, C2 Psi2, this one. And we will get the density matrix in the path basis, and we have the visibility and predictability. If we add B square plus B square, it is simply is the duality relation. There is no entanglement in between the path and the detector. So we can simply write the combined state as a product state of the path and the detector. And now if we start with the combined path and detector state, there is the detector and path state. If we have the path density matrix, we have the reduced density matrix, and the trility quantities, that is B square is this, P squared this, and E square. Here are the special cases. When D1 and D2 are identical, what happened? We can take C1 Psi1 plus C2 Psi2 product with D2. Simply, it becomes the same state with the previous cases. There is no entanglement. There is no entanglement. And if they are not identical, we will have the entanglement. Another case can happen when D1 and D2 are orthogonal. If they are orthogonal, what happens? We will have no visibility. Visibility will be 0. Only P square and epsilon squared will survive. Similarly, we can have for this case, for the three-path system or the Q-tree system, simply here we have the three combined path and detector path are correlated. The joint state can be written in this form, and similar approaches are taken. Similarly, visibility will be like this, and we'll have the trilateral relation, and similar conditions we will get, that is the identical condition or orthogonal condition as same as a two-path system. Now we will generalize these combinations for the n-path system. If we consider the n-path quantum, so it will be sum over of Psi1, Psi2, Psi3 up to n, and we will have the elements of the density matrix in this this. Here only we get the visibility and predictability, as the detector is can be written as a product state in this case. But now if we will consider in the similar fashion the quantum path detector joint state, then the terms entanglement comes into the picture. We'll have the visibility and predictability and entanglement and trilateral relations hold. Now next we will check the some noisy models like amplitude damping, phase damping, and non-Markovian amplitude damping. So we will test that whether the trilateral relations survive under the noise. Now for amplitude damping, after applying the amplitude damping operators, the resulting reduced density matrix will be in this form, and we will get the visibility bar square and predictability and entanglements, and we'll add, if we add these three quantity, they will be equal to 1. So trilateral holds, but they are redistributed. Like visibility is reduced by the term 1 minus gamma A. Gamma A is a damping parameter, and predictability also changes. Here also we see that entanglement is also changed. But in overall picture, the triality holds. We also check for the phase damping cases. Similar scenario we observe. Here only one difference is there is no change in the predictability. Predictability remains same, but visibility and entanglement both changes. But what happened after they are redistributed, but they hold the triality relation preserved. Now we'll check the in the previous cases we check the Markovian cases. We will introduce a non-Markovian amplitude damping. We will see that if we apply the non-Markovian amplitude damping, it is a reduced density matrix after the matrix evolution, and we'll get the physical. We will get the quantities, the visibility changes, predictable. Both of the three terms changes, but still they holds the triality relation. Now we will give one example, that is for the initial 2 qubit or 2-path system, the most coherent state we are taking, and initial values what we get, that is this is the like most coherent state. V square is equal to 1, and there is P square equals to 0. There is no path predictability initially, and obviously it is like it is not entangled with the detector initially. So what happened? It is entanglement is 0. And what we see after damping, what happened? Like visibility is going down, predictability from 0 to 1, it is going up, and entanglement from initially 0 and end point it is 0. In between it likes have some values. So after amplitude damping, it generates some entanglement between the path and the detector. And for the phase damping cases, what we see that predictability remains unchanged, as we see in the previous slide, that predictability remains unchanged. As in this example, P square is 0, it remains 0 all along, and just visibility and entanglement redistributed. B square equals to 1 initially entanglement is 0, and when V square is equal to 0, entanglement is 1. And for the non-Markovian cases, just entanglement and the things redistributed among themselves. Only entanglement does not reach the highest value. Now, similar scenarios we will see for the QFIT cases. QFIT cases we see that is the similar 3 QFIT cases, that it is also the maximum coherent case, and we will have the visibility initially as 1 and predictability as 0 and entanglement 0. Similar distribution we can see. And what happened, like entanglement is like in between maximum E square value is 0.5 or around, and in that case, in the previous cases, it is the entanglement we have the maximum values 0.25, that is 1 by 4. Here here is a little bit bigger, but the rest of the scenarios are similar. Like see, B square is 1 initially, here P square remains unchanged, it is 0 all along, and here entanglement is 0 initially and entanglement is 1 after a certain when gamma is 1, and when entanglement is 1, B square is 0. So this is our like this is the study. So one question may arise that whether this damping generate entanglement and damping generated entanglement in between. Like initially there is no entanglement between the system and the path if we start with a complete product state, but after, and it should be a pure state. Obviously the reduced density matrix of the path state will be a pure state, but after certain evolution it makes the density matrix, the reduced density matrix or the path density matrix as a mixed state. So we will have a little bit of entanglement. And this is the references, and this is my work that is this is in archive and under review. Thank you for listening.
Thank you for the nice talk. Any question?
Dr. Ramita, I have a small question. Yeah,
Yes.
so what we are seeing here is that with respect to the amplitude damping, when you are changing the parameter, then the entanglement is increasing and then it's decreasing. So what's happening inside the system that actually with the increase in the damping parameter, you are first observing an increase of the entanglement, and then after some time we are getting a decrease in the entanglement.
Okay. Can you see my slide now?
Yeah.
Yeah.
Okay. See what happened initially when the entanglement is 0. See the expression. There is, if amplitude damping is 0, sorry, the damping parameter initially is 0, then it remains, everything remains 0. But what happened when after a certain time, when it is not like entanglement is remains 0, but like suppose some values of gamma has certain values, these terms become not 0. Sorry, this value is 0, but we have contribution from this part. Like this is suppose it is 0.2, 0.3, and as the predictability is not 0, it is not the overall entanglement, we are getting some entanglement. But what happened after that, it becomes 0 when gamma is 1. So when gamma 1, that means we'll have the predictability, maximum predictability. Like here, see, when gamma is 1, we will have the maximum prediction, or we will get the predictability. So as this is completely predictable, so there is no entanglement or quantumness remained. Predictable means we can predict certain state, and we know that for the quantum system nothing is fully predictable. Like if we get the fully prediction, then no entanglement remains. This is how it works.
Thank you.
Ma'am, go to first page. First, visibility, where predictability and equation.
Sorry, I can you please repeat? I cannot hear.
You said that visibility, predictability, and epsilon entanglement
Yes.
square is equal to 1. Maybe these equation.
Yes.
How we can satisfy this equation? In
Okay. You want me the equation, right?
Yes.
I mean,
I read experiment this 2000 I think 18 a lot of time one experiment, like I don't have any idea. That's why I am asking about this equation. Please like satisfy this equation.
okay, you can.
I will drop in comment if
I can show you the slide that theoretically I can show, but experimentally how can you get? I have no idea, but theoretically see this slide. If you can add on these 3 terms like b square, p square, and entanglement. Entanglement is determined from this joint state. We typically do it from the concurrence. This is one of the measure of entanglement. And if we add these 3 terms like this b square, p square plus epsilon square, it gives 1. You can check. You may have. I share my archive link, and also I will share some references, if possible. Like
if something have particle nature of wave, like something high visibility, like particle nature, then other term will be 0. In experiment I just read at the time, and like something if wave nature, then predictably will high, and then other
opposite.
quantity
This is
will be 0.
opposite.
Yes.
When visible,
So
when wave, you can have the wave nature, you will have the high visibility. and when you
Yes.
have the low
Particle
I mean
nature, so high
particle nature
predictability. Yes.
yes. So
Yes.
experimentally I don't think so this is entanglement is verified. I don't have much idea. I need to check. But theoretically there is like Tabish Qureshi's paper you may follow. One there are two papers from our group, Panigrai's group, Prashant Panigrai's group. There are two, 3 papers I think. And you may also find some papers based on the system information and duality relation. This works like v squared. Maybe there may be some theoretic experimental verification. I am not that much sure. If I have some, if I get to know, I will let you know.
Yes. Okay. Thank you, ma'am.
Yeah, we have actually verified
Thank
it
you.
experimentally, not the for the tripartite, but for the wave particle duality.
Yes. I
Down.
think there is some wave particle paper I saw, but I could not remember that whether entanglement is also verified. Like
No,
the
no, no,
trility
no.
relation
That
is
is
verified.
that's why trility relation was not verified, and
Oh,
and
you
the reason
verified the
is
trility relation. Oh, nice.
no, we did not verify the trility
Okay.
relation. We verified it was long back, so duality relation was verified.
Yes.
And one of the another reason why because we used NMR system, and in NMR system the entanglement when you from the foundational aspect is not actually the it's a pseudo entanglement because not the all the particle while you are addressing are in a pure state. So there is a large background which remains in the mixed state, but there are some certain number of there is a you can associate with the purification with some amount of purification you can purely prepare some systems. So that's why even if we demonstrate, it doesn't prove from the first principle the tripartite relation. That's why we have not demonstrated at that time. But duality relation can be demonstrated, has been demonstrated.
Okay, I think further questions may be asked on chat, and it's time to move to the second talk of this session by Ankush Pandit from IIT Bhubaneswar. The title of the talk is Limits of Classical Correlation and Quantum Advantages under Anti-Distinguishability Constraints in Multipartite Communication. So I invite Ankush Pandit from IIT Bhubaneswar for the talk. Welcome to you.
Hello, everyone. Am I audible? But
You
there
are
is
audible,
much
but there is
You are audible, but there is a echo.
Now it is clear.
No, still echo is
You may try without the headphone, or just check that the headphone pin is working properly. Push it.
Yes. Hello. Okay, so I'm
Still there is echo.
Is it okay?
Speak something more.
Hello.
No, there is echo.
So I think test. Now is it okay?
A multiple echo is happening. And it's happening when you are speaking only. Means when we are speaking, there is no echo.
Hello.
So have you removed your headphone or just using the computer microphone?
Yes.
But you see that there are so many yes. And just check that you have joined only once. You are not joined two places.
Yeah.
What happened?
If you have joined from some other device as well.
No. Okay.
Or remove the phone if you are having nearby and some application might be working.
There is. I think there is no phone. Now is it okay?
Leave once
No,
and join again. I think it will work.
Okay.
Most surprising thing is that I can see Ankush as mute, but I can still hear Ankush.
Maybe he was joined from some other device as well.
Hello, now is it okay? Hello.
Yeah, it appears
Please
fine.
continue. Please continue. This is okay.
So right now it is okay, right? So can I add my headphone because it sounds better?
Sorry for the delaying. Hello.
Continue without further delay.
Okay, thank you. So I'm going to discuss my research work, which is the limits of classical correlation and quantum advantage under both distinguishability and anti-distinguishability constraint in multi-party communication scenario. So before going to the today's discussion, I would like to say thanks for the young quantum scientist organizers for arranging such kind of insightful talks. Yeah. So in a multi-party communication game, we consider
Ankush,
here
you have not shared your screen.
Okay. Wait.
Please share your screen also.
Okay. Now, is it okay?
It's fine.
We can see your screen.
So actually, you are
Okay.
still logged in as two users. Means one login as a user and one login as Ankush Pandit. Yeah. So Ankush Pandit is mute, and what we are observing is from the login called user. But you continue. This is working.
Okay. Now, basically, I'm going to consider my presentation, which is my research work, what is called limits of classical correlation and quantum advantage under distinguishability and anti-distinguishability constraint in multi-party communication scenario. So in a multi-party communication scenario, what we consider here is two spatially separated parties, namely Alice and Bob, and there is a receiver called Charlie. Now, in each round of the task, Alice gets input X, Bob also gets inputs Y, and based on their inputs, both sender Alice and Bob prepare some message, and that message sent to the receiver Charlie, which is denoted as M1 and M2. Charlie in turn performs some measurement on those incoming message and obtains an outcome Z. So in this scenario, the correlation arises between Alice, Bob, and Charlie is simply written as the probability of Z given XY, which denotes the Charlie's outcome Z, which is related Alice's input and Bob's input. Now the correlation, these kind of things and games have many number of times, and we collect the statistics in terms of the correlations. Now, in this scenario, we called that NX, NY, NZ scenario. That means the total number of input Alice received. This NY means total number of Bob's input, and NZ means total number of Charlie's outcome. Now, in classical success metric is simply given as that some linear function of probabilities with some disk coefficient, and if they are communicating with quantum states and Charlie performs some quantum measurements, then the quantum success metric will be trace of simply rho x tensor sigma y times n. Now, what we mean by a quantum advantage in a communication game? Suppose to win this game, they have to specify some strategy, or they follow some strategy to win this game. Suppose here I consider this strategy. This strategy they follow to win this game. It acts as like in each round, suppose Alice gets input 1, Bob gets also inputs 1, the Charlie's outcome should be 2. If Alice gets inputs 2, Bob gets inputs 1, Charlie's outcome should be 1, and so on. And this is Alice gets inputs 3, Bob gets inputs 1, Charlie's outcome should be 2. So these kind of things they follow for to win this game. Now we have to also consider the constraints of the communication. So there are possible constraints available to consider in the communication game, like dimension bound, parity oblivious, information constraint, energy restriction. So among these, we consider only distinguishability bound, which is a measure of the informationally restricted correlations. Now, how it works? Suppose Alice, after getting inputs, Alice sends some message to Charlie, and Charlie, based on the M1 message, can distinguish the input of Alice up to D1 probability. Similarly, from M2, Charlie can distinguish the Bob's input up to D2 probability. So D1, D2 is the distinguishability of Alice's and Bob's input. Now, if you can think that if the distinguishability of Alice's input is 2/3 and distinguishability of Bob's input is 1, then the classical success metric in the classical communication scenario will be simply 7. In quantum region, if Alice sends some quantum states and whose distinguishability is also bounded by D1, and Bob also sends some quantum states whose distinguishability is bounded by D2, then Charlie performs some POV measurements and obtains an outcome, which is this follows some same strategy, and we get SQ is the quantum success metric will be 7.1936, this number. So it simply denotes as the quantum advantage because SC greater than SQ. So this is a kind of instance that we get quantum advantage. So in order to study full quantum advantage in this kind of multi-party communication scenario, we have to characterize the correlation in terms of the probabilities. So we need to characterize the polytope which arises in this kind of communication. Now, for this scenario, which is the 3 input for Alice, 2 inputs for Bob, and Charlie's outcome for 2, here we consider Charlie has no input, or Charlie always have fixed inputs equivalently. So in this kind of communication game, we get total 12 probabilities. So in these 12 probabilities, we can think that these 12 probabilities can forms a polytope in 12-dimensional space. So polytope, which we mean that it is a bounded polyhedron and with a finite number of extremal points. So this is a simplest version of 2-dimensional polytope, this triangle. So I can represent this triangle as a polytope with 2 equivalent ways. One is I can specify the vertices, which is the origin, 1, 0, and 0. Or equivalently, I also can represent its faces side. Like this is the y greater than 0, this is x greater than 0, and this is x plus y less than equal to 1. So this, if I represent this faces side, it is called half space representation or H representation. And if we specify vertices, this is called V representation. So once we get the vertices, we can get the H representation and vice versa. And obviously it will be a convex set, because if we take 2 points inside the polytope and makes their convex combination, it will be lies inside the polytope. So the construction of the polytope for behind these kinds of communication game such that if we get the polytope, we get the facet inequality, and each facet inequality defines a game. So then we also find which facet inequality violates in quantum communication using quantum states and measurements. Not all facet inequality will violate the quantum violate the classical success metric, but yes, there still exists some facet inequality that violates the classical success metric, and then we say that yes, there will be a quantum advantage in the kind of communication game. So suppose we first study 2-2-2 distinguishability scenario. In 2-2-2 distinguishability scenario means 2 inputs for Alice, 2 inputs for Bob's, and 2 outputs for Charlie. So we get one kind of trivial facet inequalities, and we get no quantum advantage. So there does not exist any quantum state and measurement that violates this inequality, and that will be the same as the classical. Parallelly, we also study the 2-3 distinguishability scenario. We get 4 facet inequalities. Here 2 inputs for Alice and Bob and 3 outcomes for Charlie. And these 4 non-trivial class of facet inequalities still do not violate any inequality in quantum state and measurements. And in 3-2 anti-distinguishability scenario, so unlike the distinguishability scenario, you also study what happens in the anti-distinguishability scenario. Here, Charlie's task is to anti-distinguish both Alice's state and Bob's states. So in 322 anti-distinguishability scenario, I get only one non-trivial class of facet inequalities, and in quantum regime, it is still not violate. So then comes 322 distinguishability scenario. In 322 distinguishability scenario, we get total 6 facet inequalities, these facet inequalities, and each facet inequalities defines a game. The first two inequalities is a trivial class of facet inequalities, and we get no quantum advantage. And then these 4 facet inequalities are violates the in quantum scenario. So in quantum region, SQ is greater than SC. So now how we how we quantify the quantum advantage. So first we characterize the polytope, then we characterize the facet inequalities, and we then characterize the classical success metric, which is a linear function of probabilities in the classical scenario. Then jumping from the classical scenario using Bond's rule by quantum state and measurements is replaced by in this probability function, and Charles also performs some optimal quantum measurements. So we define the quantum success metric is this. So we define the quantum advantage if the ratio of quantum success metric by classical is greater than 1. Another one is we ask the question, if SQ is greater than SC, then how much distinguishability and anti-distinguishability needed in kind of classical communication scenario to achieve SC is equal to SQ is equal to a simple S? That's our question. So that ratio will be also 1, and no advantage if SC is equal to SQ, and this will be equal to 1. So we use seesaw semi-definite programming to find what is the maximum value of the quantum success metric. As we know that this seesaw iteration always gives a lower bound of any success metric in quantum regime. So we first optimize this SQ, keeping fixed, because this is a non-linear. It is a nonlinear quadratic function. So keeping fixed Alice state and Bob states, and optimize over Charles measurement, and such that the measurement is greater than 0 and sum of them is identity. This is a POVM constraints, and optimize over all possible Charles measurements, and we get the best Charles measurements. And we fix the next, that the Charles measurement is fixed, and we optimize now Alice state. So we also have to fix the Bob state also. We optimizing the Alice state such that rho is greater than 0 and trace of rho is 1. Similarly, once we get Alice state and Charles measurement, we fix this one and optimize our Bob state like before, which is greater than 0, and trace of sigma y is equals to 1. So we have to keep in mind, we also have to bound the distinguishability of Alice state and Bob state. For that, we have introduced two auxiliary variable, which is named as theta and gamma, which is greater than 0, and trace of that value is upper bounded with D1 distinguishability, and similarly for Bob, and similarly for Bob, trace of gamma is less than equal to D2, that is upper bounded with D2. So suppose this facet inequalities defines a game. So I take D1 is equal to 2/3, D2 is equal to 1, SC will be 3, and using seesaw optimization that I said before, we get say SQ is equal to 3.1936. This shows the quantum advantage, and in order to find SQ is equal to SC, that will be the total distinguishability in classical communication divided by quantum communication, which is greater than 0, which is also a quantifier of our quantum advantage. So this clearly shows that we have also a state and measurement in quantum communication that violates the classical system, and this shows a clear quantum advantage. Now we also parallelly studied the 2-to-4 anti-distinguishability scenario. We get lots of facet inequalities and we get lots of games, and out of this, not all facet inequalities violates the quantum scenario, but these three facet inequalities shows quantum advantage over the classical one. In 2 to 4 anti-distinguishability, here Alice gets inputs 2, Bob gets also inputs 2, and Charlie has 4 outcomes. So here I considered some states and measurement that violates the inequality and provides the quantum advantage. Suppose, for instance, Alice and Bob, they sends these two states. This is the rho 1, rho 2 Alice states, and sigma 1 and sigma 2 is a Bob state. And if Charlie performs a measurement which is given as this, psi 1 and psi 2, psi 3 is written as this, then SQ, if we put in the Bond's rule, trace of rho here, if we put in the rho x, sigma y, and mz, then we get that SQ is equal to 1.46, and rho 1, rho 2, and if we check the distinguishability here, we will get 0.85, and if we put here, we will get classical success metric is 1. So the ratio will be 1 greater than 1, and this is an instance of the quantum advantage over the classical one. So we also try to figure it out how much distinguishability and anti-distinguishability region where we get the quantum advantage. In 3 to 2 distinguishability scenario, we get the quantum advantage over this region, but when we go beyond the 0.72 and D2, any value of D2, then we get no quantum advantage. Almost all possible, all three scenarios. So this is just because of asymmetry of inputs. And if we check the quantum advantage over the anti-distinguishability scenario in 2 to 4 scenario, we'll get quantum advantage in almost whole region, and most quantum advantage for the first inequalities lies this, and second inequalities lies this, and so on. So it depends on the which inequality we are considering and which game we are performing. So later we also study the anti-distinguishability of distributed inputs, which is a analytical study we already also did. So here we consider n senders. N specially senders, they receive some inputs from outside, and based on their inputs, say each senders send some message to the receiver, and receiver performs some measurements and obtain outcomes. And here the constraints of the communication game that each receiver's input is bounded up to A1 value, such that the receiver cannot anti-distinguish the inputs, each sender's input up to A1. More than A1 is AI is not possible. So we get the classical bound is given by this. Later, we also move motivated from Pivier's theorem, we also get the for n senders, the classical anti-distinguishability divided by quantum anti-distinguishability is greater than 1. So with theta is varied with this region. And if we can see this, so after some simple calculation, you will see for n senders, we'll get the exponential quantum advantage. And if n tends to almost infinity, it will AC by AQ to the power n, it goes to 2 to the power n. So we also using.
Please
Yes.
conclude. Yeah, I request you to conclude in couple of minutes because it's
Okay. Yes, sure. So in this figure, we consider the quantum advantage for using semi-definite seesaw programming. We check for 2 sender. So we give the theory for n sender. Here we take 2 sender, and each sender has 3 inputs. We'll get this blue line plot. And if we increase the input and keeping the senders, all the senders fixed, we'll get some little bit amount of advantage, this orange. But if we fix the inputs, n, small n is fix the inputs, and we increase the senders, and we'll get there is a blow up of the advantage that is represented in the yellow line. So in summary, in this article, we investigate multiple multi-sender and one receiver communication scenario where the constraints of the communication game is distinguishability and anti-distinguishability constraints of the sender's input. And the interesting thing is the receiver has no input, still will get advantage. The first scenario comes by Navaskas and Vartisi. They bound the dimension of the communicating system. Here we bound the distinguishability of the communicating system. And we also characterize the set of the classical correlation. From there, we derive the facet inequalities that defines its boundary, because each facet inequality is a game. And we derive the facet inequalities in terms of D1, D2, which is the more complex. And later we also analytical study for the unbounded quantum advantage, which blows up with the centers. So these are the reference, and this is the paper. So this paper is accepted in PRA. Thank you for your attention.
Thanks for
Sir,
the nice talk. Yeah, please.
sir,
Thank you.
I need a little concept. Just move to first slide, please.
First slide. Wait.
Oh, sir, here you tell that Alice and Bob. The second slide, please. Yes.
Huh? This one.
Second slide. Yes, second slide.
Okay.
Next slide. Yeah, sir. Yes. Oh, no, behind one slide. Yes. Yes. Okay.
This
Sir,
one or this one?
yes. Just behind, sir. Sir, here you explain that sorry, 2 and 1 Alice and Bob input, and 2 is Charlie. Okay. So here in 48 orbit size, like something 2p.
This
2p.
one.
Yes. I want to. I need to concept about this 2p, and in first slide 3p was there mentioned. Would you like to give me a concept about that?
Okay,
This,
so
3p
basically so
it's
in this
numerical factor,
slide,
like
the 3p is because hello.
It's
Yes.
numerical factor.
Yes, I'm saying that. So actually, is this 3p because I write these things are in terms of the probability of outcome 1, and 3 terms because of these probabilities are weightage is so the weightage is larger than other weightage. That's why the 3 factor counts. And here, so this we got from the numerical calculation from several available software. So here you can the -2 you can simply write as -2 times 1 minus probability of outcome 1, and then all the terms will be positive. And this not in our hand to get the facet inequality. This is purely computational part. There are also available.
Why in first term 24 size orbit we did not use any
Actually, orbit size means we only get the minimal non-trivial class of facet inequalities. So this orbit size represents this facet inequalities appears 24 times. So we'll not get 24 times facet inequality. We will only 1 times facet inequalities. Okay, so these facet inequalities appears 48 times. So we only take 1 times. So that's why this is orbit size.
Okay, thank you.
Okay, maybe further question answer can go on the chats because we are running behind the schedule. So I invite Rashid join from Delhi Technological University. for our next talk. The title of the talk is Geometric Quantum Discord and its Application in Quantum Key Distribution. So over to you, Rashi Jain from Delhi Technical University.
Good evening, everyone. Sir, I'm not able to share my screen.
Yeah, I think you should share. Okay.
The previous speaker has to first unshare the screen.
Yeah, previous speaker. May I request Ankush Pandit to stop sharing? Yeah.
It's there. It's done. Means please go ahead. Rashi?
Yes, sir. Yes, sir. Sir, is my screen visible?
Yes, but make it full screen.
Yes.
Continue. Please speak.
Okay. Good evening, everyone. My name is Rashi Jain, and I'm currently pursuing my PhD under the supervision of Dr. Satyaprata Adhikari from the Department of Applied Mathematics, Delhi Technological University, Delhi. Today, I'm present here to deliver my talk on the topic Geometric Quantum Discord and its applications in quantum key distribution. So, as we all know, entanglement serves as a key resource in quantum key distribution protocols. There may exist quantum correlations other than entanglement that may be used in quantum key distribution protocols. We know that separable states also contains quantum correlations. So in this regard, in 2010, Dakik et al. Proposed the analytical formula for the calculation of geometric quantum discord of two tensor two-dimensional systems. They considered the generalized state rho AB to tensor 2 and calculated its geometric quantum discord, which is given by the formula DG 2, 2. From this work, we obtained the motivation that there should also be a formula that could calculate the quantum correlations in arbitrary dimensional systems. So to quantify the amount of quantum correlations in arbitrary dimensional systems, that is D1 tensor D2 systems, we first...
Screen is not leaving. Yes, okay.
Is it okay?
Yes.
Yes, it is
Now
okay.
screen
Okay.
Okay. So we first consider a two-qubit state, which is given by rho AB 3 tensor 3. We calculated its geometric quantum discord, which is given by DG 3, 3.
Again, screen not visible. I think I have issue. Yeah, everyone.
No, the screen is going off frequently.
It's going off. Sir, is it fine now?
No, it's not fine.
Not yet.
No, Rashi, don't be tensed.
Sir, actually it is raining over here, so there might be some network issue due to that.
No, but you are audible properly.
I don't know, sir. Shall I continue?
Yes.
It's now you are there. It's visible again.
Okay. So the geometric quantum discord of 3 tensor 3-dimensional system is given by DG 3, 3. Now we extended this concept to the arbitrary dimensional systems, that is D1 tensor D2 dimensional systems, by considering the generalized D1 tensor D2 dimensional state given by rho AB. Upon calculating its geometric quantum discord, we found that it can be given by DG D1, D2. Now, in this work, we use the derived analytical formula for the geometric quantum discord of arbitrary dimensional systems in studying the
not leaving.
concept. In studying the concept of quantum key distribution schemes. We discussed the case for the successful generation of the secret key when the communicating parties share quantum states, which are the private states. I will explain the concept of private states in the next slides. We have also introduced the relationship between the distillable key rate, which is given by KD, and the geometric quantum discord, which is given by DG. So first, let me explain the generation of the private states. So let us consider a 4-qubit state, which is given by rho AB, A prime, B prime, which is shared between the two parties, Alice and Bob. Alice and Bob are the distant parties. The qubits A and A prime belongs to Alice, and the qubits B and B prime belongs to Bob. The qubits A and B contribute to the key part of the system, whereas the qubits A prime B prime contribute to the shield part of the system. The qubits A prime B prime which contribute to the shield part are designed such that upon application of a certain operation, these qubits get traced out and the key part gets additional security. In the previous works, the states of the shield part of the systems were considered to be entangled states. But in this work, we explicitly consider the shield part to be separable states also. So now, the 4-qubit state rho AB A prime B prime can be expressed as the convex combination of the 2-qubit Bell states and the d-tensor d-dimensional quantum states which are given by sigma i's. In the matrix form, the state rho AB A prime B prime can be expressed as a 4D square cross 4D square matrix, where each element is also a matrix. So now, when we apply a twisting operation on this state, what do we obtain? So let me first explain the application of the twisting operation on this. So we first consider the first element of the 4D square cross 4D square matrix, which is sigma naught plus sigma 1. We write it in the form of singular value decomposition, where V1 and V1 dagger are the unitary matrices and D1 is the diagonal matrix which contains the singular values of the chosen element. Upon application of the twisting operation, we find that it can be expressed in terms of the trace norm. Applying the twisting operation on all the elements, we obtain the private state which is given by sigma AB, and this can be given as a 4 cross 4 matrix which is in terms of the trace norm. Now there might be an eavesdropper present in the protocol who may try to attack this private state with the motivation to extract information about the secret key that is being formed between Alice and Bob. Upon Eve's intervention, the shared composite system is given by psi ABE. Here, the parameters x, y, z, and w are given in terms of the trace norm. Now, using these parameters, the distillable key rate is defined as Kd in terms of x, y, z, and w. We use the relationship between the trace norm and the Frobenius norm, and we find the lower bound for the distillable key rate, which is given in terms of the geometric quantum discord of the states sigma naught plus sigma 1 by 2 and sigma 2 plus sigma 3 by 2. To ensure the positivity of this lower bound, that is to ensure the positivity of the protocol that the secret key is definitely established between the two communicating parties, we find that the geometric quantum discord of the state sigma naught plus sigma 1 by 2 should belong to the given interval. Now, for example, let us consider a state var rho, which is expressed as the convex combination of the 2-qubit Bell states and the d-tensor d-dimensional. Here we are choosing d as 2, so the 2-tensor 2-dimensional quantum states which are given by sigma naught, sigma 1, sigma 2 and sigma 3. Here sigma 1 and sigma 3 are separable states. So when we calculate its distillable key rate, we for the graphical representation, we find that the geometric quantum discord of the state sigma naught plus sigma 1 by 2 is a constant, and the geometric quantum discord of the state sigma 2 plus sigma 3 by 2 is given in terms of the parameter m. As the value of the geometric quantum discord sigma 2 plus sigma 3 by 2 increases, the lower bound of the distillable key rate also increases. So to summarize, we have derived an analytical formula for calculation of the geometric quantum discord of two Q-trade systems, and then we have generalized it for arbitrary dimensional systems. We have applied the concept of geometric quantum discord in quantum key distribution protocols, where the communicating parties makes use of private states for the generation of the secret key. We have also found the lower bound for the secret key rate Kd in terms of the geometric quantum discord. We have also found the bound for the successful completion of the protocol of the geometric quantum discord of the states considered as the private state. So to summarize, we have found that geometric quantum discord can serve as a valuable resource in quantum key distribution schemes, which broadens its scope for secure communications by offering alternatives to entanglement-based systems. These are my references. Thank you.
Floor is open for questions. If you have any questions, you can unmute and ask.
So any questions?
Ma'am, you explained very well, but there was a issue on screen. We can't ask any question.
Okay.
Hi, Rashi.
Hello.
This is Sheikh. I have a question.
Yes.
Topic was
So,
very
just
interesting.
a simple question. So, this kind of advantage, the concept of private estate and other things has also you have tried to explore in simple discord instead of quantum geometric discord.
No, sir. We have only worked in geometric quantum discord.
Okay. Any insight that it should
Ma'am,
work there as well?
I need this presentation. Ma'am, I need this presentation.
Sure, I can email it to you.
Okay.
This work is also published in Physica Scripta. You may refer it from there also.
Just share the Physica script link in the chat box and Mukaram.
Okay, sir.
Yes. Yes. Thank you, ma'am. It was very interesting. That's why I want to visit again this.
Okay, thank you, sir.
Oh, thank you, ma'am.
Any other questions? If not, then we can go to our next talk by Sonia from Delhi Technological University. The title of the talk is Entanglement Detection by Using Nonlinear Witness Entanglement Operators. So, invite Sonia. Over to you.
Is my screen visible?
Sonia, your screen is visible, but you are not.
Okay. Am I audible?
You are audible, your screen is visible, but you are not visible.
Okay, sir.
So if your internet is, you are confident on your internet, then switch on your camera. Otherwise, you can continue in this way.
Okay, sir. Sure, I will be continuing without video.
Okay, please go ahead.
Good evening, everyone. Myself, Sonia. I am pursuing PhD from the Department of Applied Mathematics of Delhi Technological University. My broad area of research is quantum information theory. Currently, I am working on the research topic entanglement detection through nonlinear entanglement witness operator. This is the basic outline of my presentation. Before going towards my research work, I will be first explaining the basic concept that I have been using.
Maybe you use the full screen mode. You see on the screen right hand side, yes. Yeah.
Is it visible?
Yes, it is.
It's fine. Means it's I can see it properly.
Okay, sir.
Please continue.
Okay, before going towards my research work, firstly, I will be explaining the basic concept that I have been using. Basically, in information theory, it gives us a mathematical framework through which we can study about the communication and the correlation when some capacity and the bounds are established on this system. Generally, there are two types of information theory: classical information theory, in which we study about the information over the classical system. Generally, it takes the unit, bit is a basic unit. However, in other one is a quantum information theory. In case of quantum information theory, quantum state describes the condition of the quantum systems which are generally associated with the Hilbert space. In case of two-dimensional Hilbert space, basically the unit for the qubit, basically the unit for the quantum information is qubit, which is a superposition of the two classical bit represented as alpha time ket 0 plus beta time ket 1, where alpha and beta are the probability of the states collapsing on either onto the ket 0 or other one on the ket 1. Generally, the quantum system is in two types of state, either in the pure state or either in the mixed state. Pure states are generally represented by the state vector. Therefore, arbitrary state vector psi is said to be in pure state if it can be written in the form of like this, and is in mixed state if it can be written as a convex combination of the pure state. In order to represent the mixed state mathematically, we use a operator known as density operator, which satisfies the following three properties. Since we want to study about the correlation, therefore this leads me towards the definition of the composite system. Therefore, a system is said to be in composite system if it can be written as a tensor product of two separate subsystems. When two systems are combined, their measurement outcomes may or may not be dependent. Either there may be a classical correlation, there may be a quantum correlations. Therefore, this leads me towards the entanglement. Therefore, in terms of correlations, a quantum system is divided into three categories. Either it is in either there may be a classical correlation or there may be a quantum correlation. If there is no classical correlation, then the system is said to be in product state, and it can be written as a tensor product of two separate subsystems. If we can write it as a in this form, then it is said to be inseparable state, as the state is said to be in entangled state. This is the simplest example. Clearly, this system can be written as a tensor product of two separate subsystem. Therefore, it is a separable state. But in some examples, for example, in Werner state, it is hard to write them by definitions. Therefore, this leads us towards the some separability criteria for detection of entanglement. Currently, I am focusing on the entanglement witness criteria. Therefore, generally all the quantum states form a convex set, and the separable state lies in this convex subset, and the entangled state lies outside this set. Therefore, by using the Hahn-Banach theorem's corollary, it was found that entangled state can be separated from the separable state by using the linear functional. And this linear functional corresponds to the entanglement witness operator. From it, we can see that this linear witness operator is detecting this part of the entangled state. We do not know anything about this part of entangled state. This motivated us towards the non-linear entanglement witness operators. Therefore, many works has been done till now in order to detect entanglement by using the non-linear entanglement witness operator. In my work, I am using the linear witness operator through in constructing non-linear entanglement witness operator. This is the simplest construction that I have been currently showing. Since my work is unpublished, so I am not showing all the constructions. This witness operator is satisfying the two properties that are useful that will be useful for a witness operator, that is trace of W rho-sep is greater than equals to 0, and this is the simplest example detected by this witness operator. Thus, this witness operator is satisfying the two properties and hence is acting as a non-linear entanglement witness operator. Basically, we are showing the non-linearity of an operator in our research work. These are my references. Thank you.
Okay, so thanks for the talk. Any questions? If there is no question, maybe we move to the last talk of the session by Kunika Agarwal from SN Bose National Center for Basic Sciences. The title of the talk is Complementarity Revisited, How Preparation Shapes Incompatibility. So I invite Kunika. It's over to you. And yeah. Hello. Is Konika Agarwal available here?
I think I'm not seeing Kunika in the chat box. Let me try to connect with her.
Yeah, because last talk ended. Maybe we wait for a few minutes.
I think in the meantime, if some participant get question with the other speakers, then they can ask in this time.
I think there might be network issue or something, so we cannot contact her yet. So maybe we wait for a few minutes and then we decide.
Hello.
Yes.
Hello. Sir, are you
Yes.
waiting for me? I'm sorry.
Yes, we are waiting
Yeah.
eagerly for you. The last talk finished little
Oh,
early.
I thought it was supposed to start at 8:50. So
That's true,
actually,
but
no,
in any
actually I was
meeting
at
we expect there can be many things, but you should join little before. It's not exactly just those stories of the poets. Like I recite my
no,
poem
no,
and I'm listening somebody else's poem.
no, I understand, sir.
Mm.
I'm really sorry.
No, please go ahead
Yeah.
Okay.
share
Please
your
start.
Yeah, sure.
Yeah.
Just a minute. Can you see my screen? Like, is it presented?
Yes. Yes.
Yes, it's
Yes.
perfect.
Yeah. Hello, everyone. I'm really sorry for the delay that I've
It's
caused.
perfect, man. But
Yeah.
if you are confident on the internet speed, then you can switch on your camera too. But
Oh,
if you
yes,
are
yes, sure. No, yes, sure. Yeah. Can you see me?
perfect, but make
Yeah.
full screen once
Okay.
again, and then please continue.
Yeah. Okay. So, hi everyone. So, my talk is based on complementarity revisited, how preparation shapes incompatibility. So here, if you can see that these are pictures of Neil Bohr, and this picture actually tells the result that I'm going to talk about. So here you can see that there are two qubits which are in the same configuration, and these are the two qubits which are in opposite configuration. And there is something that you can do with these opposite configurations that was not earlier known to be possible. So this talk is based on two papers, particularly this quantum incompatibility in parallel versus anti-parallel spins, which has recently been accepted in PRL, and this another work that we have recently done and put it on arXiv. These are all my collaborators in this work. And so I would like to start with classical, since we are talking about incompatibility, I would like to start with classical measurements. So let's say we take two measurements which are color and shape. So I can always individually know what is the color of a particle and the shape of a particle or a object. So let's say here I want to see whether the color is red or green. And here I want to see whether shape is circle or triangle. So that then I can always write my measurement like this. Now in classical mechanics, it is always possible to jointly measure these two observables, or any observables I can always jointly measure. That means that I can always make a bigger measurement set, and I can always do this in my lab. Now, if I go to quantum measurements, so this is one example. These are two examples of quantum measurements, which is one of them is Pauli Z, and another is this Pauli X. And in general, the quantum measurements follow this rule. This is the most general definition of quantum measurements. But is it possible for us to say that all quantum measurements are jointly measurable? Or I can create some parent POVM and jointly measure these two observables? That Niels Bohr 100 years ago told that that is not possible, and that is the complementarity principle, that there exist observables which cannot be jointly measured. To illuminate on that, I would first like to give the definition of what we mean by joint measurability. So let's say I have a measurement box M1 which has K outcomes, and another measurement box M2 which has L outcomes. So if there exists a parent POVM, M parent, with at least KL outcomes, such that using classical post-processing, I can get the statistics of M1 and M2, then I will say that M1 and M2 are jointly measurable or compatible. If they're not, then I will say they're incompatible observables. Now, to give a picture of this, you can see it like this, that in each round, Alice gets a state row. She applies this parent measurement, gets some outcome. Another round, she gives the state row and gets some outcome. And all of these outcomes she collects. And at the end, here, what she does is she does a classical post-processing and gets the outcome. So if the measurement was first measurement, then what is the probability of getting the up outcome, down outcome, like that. So this is the intuitive picture of what happens when we are talking about incompatibility of measurements. So now, as an example, we can see, as I earlier also said, that sigma z and sigma x are not jointly measurable; they're incompatible. But is there any way such that I can make them compatible? So what I can do is, we can always add some noise to the measurement. So let's say I have a faulty measurement, and what that faulty measurement or noisy measurement does is, with some lambda probability, it does perfectly sigma z measurement. But with 1 minus lambda probability, it randomly gives an outcome. So this way I can define both my sigma z lambda and sigma x lambda measurements. So of course, they won't give me the perfect statistics of z and x, but that is the best I can do if I can use only one single machine to get the statistics of both. So it was shown by Paul Bush. So of course, the next question is, what is this maximum probability that I can get here? So this probability I will also call sharpness threshold. So Paul Bush showed that for sigma z and sigma x, you can take the maximum lambda up to 1 by root 2. And in this regime, between 0 to 1 by root 2, your sigma z lambda and sigma x lambda will become compatible, even though they are commutating. They are non-commutating. Similarly, we can ask the same question for 3 observables, x, y, and z. Again, they are not compatible. Again, we add noise, and there's another 0 to 1 by root 3 range where they become compatible. So this all work was done in 1986, and there have been many works in incompatibility relating it to other areas as well. But in 2016, scientists actually generalized the notion of joint measurability or compatibility, and they defined something called k-copy compatibility. So what the picture here is that in each round now, instead of getting the state rho, Alice gets k copies of rho. And she has to jointly measure a set of n observables and get the statistics on the single state row. So what she does is, again, she takes the k copies, can perform some measurement, parent measurement on that, and later again using classical post-processing, she can give the statistics of n observables. But is this, so for example, let's say I want to do x and y measurement, and I am given 2 copies. So this is 2 copy compatibility. So in that case, that very trivially Alice can do that, because on the first copy, she will do the x measurement, and on the second copy, she will do the y measurement. So she will get the statistics of x and y both for rho, for any state rho. But what happens when I take more than 2 observables here? So let's say I take 3 observables, which are x, y, and z. So one way to apply measurement on this is individually, again, I do x measurement, y measurement, and I do not do z measurement. So we don't get any information about the z measurement here. So my lambda actually comes out to be 0. So here lambda is actually a very good measure of incompatibility. So can we do something better? So Paul Bush taught us that you can apply some noise and make a noisy YZ measurement here. So if they do this, so then they get a sharpness threshold which is better than what they had when it was only a single copy of the state. But this is not, is this the maximum? That should not happen. So what is the maximum here? Because this is not the most general measurement. So most general measurement would be an entangling measurement, which takes the 2 system as a whole. And there they showed that your sharpness threshold becomes √3/2, which is the maximum in this case. But again, this is not perfect. So as I showed in my first slide, we are here going to talk about the anti-parallel configuration. So my obvious question from here is, what happens if instead of taking parallel configuration, I take anti-parallel configuration and then try to see what is the sharpness threshold? Will it be equal? Will it be greater? Will it be lesser? We don't know anything till now. So in this work, we have answered that question. And we show that if you take the set of observables to be x, y, and z, then on anti-parallel configuration, they become completely jointly measurable, perfectly jointly measurable. So the lambda here becomes 1. And it's not just these observables. If I take the 4 tetrahedron directions and take the projective measurement and take those projective measurements, those are also perfectly jointly measurable. Now, we can also ask this, that are these the only configurations which give me this advantage? So one thing that we have ruled out is that if you take the configuration to be row tensor sum CPTP map applied on the other second copy of the state, then you cannot get any advantage beyond parallel configuration. But of course, this is not all. There is still some scope to get more. So now this all result is a theoretical result. Is it possible for me to verify all of this in a lab, in an experimental lab? So we propose that, okay, so for that, of course, and I cannot go to an experimenter and tell them that, okay, you check this on all states. And that is not possible. There are infinite states. So of course, I have to provide them with a finite number of states. So what states I should provide such that they can perform this experiment in lab? So we check that if you take the states from a great circle, or if you take the 4 tetrahedron pure states, then you cannot show anything in your lab, because anti-parallel and parallel configuration give you the same thing. But if you take this octahedron, regular octahedron inscribed in the Bloch sphere, and take the pure states, then there you get to see the difference between anti-parallel and parallel configuration. So with a very limited states, we can actually verify this in the lab. Now, moving on. So there's always this question that is anti-parallel always better than parallel in joint measurability sense? We do not have a definite answer, but we do believe that is the case, and we have our reasons to believe that. So as I showed you in the earlier slides, my theorem 1 and theorem 2 show that if I take the observables to be XYZ or the tetrahedron 4 observables, then anti-parallel gives me, anti-parallel helps me to achieve perfect statistics for them, to get perfect statistics for them. We also tried to see other measurements. So particularly we tried three observable sets. So what we did is that if you take the T state and take 3 observables very symmetrically from there, then we tried to see what happens here in anti-parallel and parallel case for all theta. So what we see is this. So this red plot, this red line is for anti-parallel, and the blue plot is for parallel. So here you can see that anti-parallel has a very large range where the lambda is actually 1. And then after that it dips, but it is always more than the parallel configuration. You can also see that there is this point where parallel and anti-parallel actually, the plot actually meets. And this theta is exactly 90 degrees, and this is not a coincidence. So what we so at 90 degrees, what happens is all these three observable directions, they come out in a great plane. Now we know that in quantum mechanics, a universal flipper, let's talk about qubit, a universal flipper does not exist. But if I take the states from great plane, then a flipper exists. So that is what is playing a role here. So if I take any n observables from the great plane, then my parallel and anti-parallel configuration give the same results. So the sharpness threshold does not change for observables which are coming from the great plane. In the 2016 Carmeli paper, the people who actually defined the k-copy compatibility, they also asked another question. So they defined a quantity called index of incompatibility. So what they're asking is that if I give you a set of observables, let's say n observables, what is the minimum number of copies that I require, minimum number of identical copies I require so that I can get the perfect statistics? Or is it possible that there exists a set for which this is maximal? So that means the number of copies required and the cardinality of set is same, n. So they were able to show an example this XYZ, because XYZ you cannot get perfect statistics with 2 copies. So with 3 copies, you can trivially get it. So they were able to show an example, but not able to answer the question in general N. So here we were also able to show that if you take any N observables in any direction, using only N minus 1 identical copies, you cannot get the perfect statistics. If you're taking identical copies, you have to take them all. You have to take all N of them. So that was one result. Then all of these results actually made us rethink about the order of incompatibility. And this is actually our next work. So to define the order, first I have to quantify incompatibility or complementarity here. So first of all, my first measure is actually here the sharpness threshold, which is for, let's say, for an observable O, the sharpness threshold is lambda O. So if I take the observable sets O and O prime, then I can always get the sharpness threshold for both O, which will be lambda O, and lambda O prime. So if the sharpness threshold of O prime is greater than that of O, then I will say that O prime is less incompatible than O, or rather O is more incompatible than O prime. For example, to make it a little simpler, so let's see an example. So if I take the set O to be just X and Y observables, then my sharpness threshold is 1 by root 2, as we saw earlier. And if I take the O prime, the set O prime to be X, Y, and Z, then the sharpness threshold is 1 by root 3. So now that means that the XYZ set, that is more incompatible than the set X and Y. So this is one way you can always give ordering to the observable sets, incompatibility ordering to the observable sets. But what happens in the anti-parallel case is that this ordering does not remain there anymore. So let's say I take the observables from a great plane, 3 symmetric observables. So this is trine directions. So these are 3 observables here. I take another set to be the tetrahedron, so symmetric tetrahedron in the Bloch sphere, and these are the 4 observables. And I take XYZ, or MUB, you can also call it. So here, of course, in this trine case, the parallel and anti-parallel lambda threshold, sharpness threshold, will remain same as we saw in the previous theorem. And here we saw that tetrahedron and MUB, the anti-parallel gives you perfect sharpness threshold. But what we see here is that if you notice, okay, one more thing. So I will denote this 3 means actually 3 identical copies. So here any N if I write, so that means N identical copies. And this 1 actually means that 1 copy of the state and 1 orthogonal counterpart of that state. So, so the ordering actually changes like this. So if you take anti-parallel configuration, then here it is perfect 1. Lambda is perfectly 1. Here lambda is lesser than 1. So this set is more incompatible than this set. But now let's say I take the configuration with 3 identical copies. Using 3 identical copies, I can perfectly measure this set, but I cannot do that here. So as I change the preparation, the order of incompatibility between these 2 sets have changed. Similar thing also happens here. So again, if I take anti-parallel configuration, this set is more incompatible than this set. But if I take 2 copies of the state, then this set is more incompatible than this set. So again, preparation of the copies, like preparation of the qubit states, actually have changed my incompatibility order. And this is something that we call the no comparison theorem. So the take-home message from here is that my incompatibility does not only depend only on the observables. It actually depends on how you are preparing your copies. Are you preparing them in parallel or anti-parallel configurations? Moreover, we are able to show that using 2 qubits, like some encoding of 2 qubits, you are able to get the perfect statistics of all x, y, and z for that state row. And the Bose complementarity principle is actually a 100-year-old principle, and we have never seen a no comparison kind of result before that. So this is the first time we are showing that the hierarchy that we have had in complementarity, that is not there anymore as soon as you get into multi-copy compatibility. Yeah, with that, I would like to end the talk. Thank you so much.
Okay, thank you for the nice talk. So, is there any questions?
Participants, if you have any questions, you can unmute yourself and ask your question. And if there is any issue with the mic, you can also type in the chat room. Even if you are listening from YouTube, you can write there. We'll bring the question here. So it seems you were very clear. There is no question. But even at a later stage, if you feel a question, you can send us the questions and I can share it with the speaker, or you can directly contact the speaker. So it's the end of the day, and it's my pleasant duty to thank the last speaker, Punika Agrawal, as well as all the speakers of this session and the first session, and also a special thank to both the session chairs, now Dr. Shrudeep Haldar, and in the beginning, Dr. Vaibhav Raut has chaired the sessions, and we're thankful to both of them. And of course, we are thankful to all the audience who are listening this talk, interacting, and making this event successful. So thank you all, and we'll join back tomorrow morning.
Hello, sir.
Tomorrow evening at 6
No,
p.m.
sir, I think someone is trying to ask.
Okay, Mukharam, do you want to ask something?
Yes, sir. I want to ask a question from you. If we need presentations from all speakers,
So
then
that request has to be made to the individual. Means as an organizer, we don't know what is copyrighted, what is not. But the other thing is that one easy thing is that you can visit the YouTube link again, and all these things will retain in YouTube, but not the PPTs, but that the presentation, the way you have seen. So you can revisit if you want to see it once again, a particular slide you want to see, you can visit in the YouTube and go to
sir,
that.
actually, I want to save in my laptop for record. That's why I will visit when I want to
If you
read
want
this
something
topic.
specific from a speaker, just drop a message to that speaker in the chat room or separately. And for your convenience, you
Okay,
can visit
thank
the
you,
YouTube
sir.
and see it again.
Okay, thank you, sir.
Any other opinion, any comment, anything, any questions to any speaker? So it seems there is no further question. So we hope that we will meet again with everyone at 6 p.m. Indian time tomorrow. So good night and see you tomorrow. Bye.
Bye.